we measure with rulers, with meters and miles, but in the universe, those numbers dissolve. Tonight, we ask a simple question, a vast question. What is the biggest thing in the universe? As you lie here, listening to these words, your body occupies a tiny fraction of Earth's surface. Your height, perhaps close to 2 meters, seems substantial enough for daily life. You navigate doorways, furniture, and the spaces between buildings with an intuitive sense of your own scale. This human dimension is our starting point, our reference frame for understanding everything else. But beyond our immediate surroundings lies a world of increasing magnitude. Buildings reach hundreds of meters into the sky. Mountains stand kilometers tall. Oceans stretch thousands of kilometers across. Already, we begin to lose our intuitive grasp of scale. When night falls and we look upward, we glimpse something more. The stars, appearing as mere points of light, are actually enormous spheres of plasma, many larger than our entire planet. The distances between them are so vast that we measure them not in kilometers but in light years. The distance light travels in a year, moving at nearly 300,000 kilometers per second. How can we truly comprehend such scales? The human mind evolved to understand sizes relevant to our survival, from the smallest seeds to the largest predators. But the universe exists on scales far beyond these. We need new metaphors, new frameworks, new ways of thinking. Tonight, we embark on a journey of scale. We will begin with ourselves, with the human perspective, and gradually expand outward, from the tallest mountains to the widest planets. From stars to galaxies to superclusters of galaxies, we will trace the largest structures known to exist, vast networks of matter, stretching across billions of light years. Throughout history, our understanding of what constitutes the biggest thing has continually evolved. Ancient peoples saw mountains as the largest features of existence. Early astronomers recognized that Earth itself was far larger, and that the sun dwarfed our planet. Modern cosmology has revealed structures of such immensity that they challenge our very conception of what bigness means. This is not merely a journey of numbers growing larger, it is an exploration of how we situate ourselves within the cosmos. Each level of scale reveals new patterns, new relationships, new ways of seeing our universe. What appears chaotic at one scale may reveal profound order at another. As we drift through these expanding scales, we might feel increasingly small, but there is something profound in this smallness. Something humbling, yet empowering, about recognizing our place within this vast tapestry. We are made of the same elements as the stars. We are participants in the same cosmic story. The night sky above you now contains light that has traveled for millions, even billions of years to reach your eyes. Photons that began their journey when Earth was unrecognizable, or before it even existed. When you look up, you are looking not just outward in space, but backward in time. Our quest to understand the biggest things is relatively recent. For most of human history, we lacked the tools to see beyond our immediate surroundings. Only in the last few centuries have telescopes extended our vision to distant planets and stars. Only in the last 100 years have we discovered galaxies beyond our own, and only in recent decades have we mapped the largest cosmic structures. This continuous revelation mirrors our own growth as a species. As our instruments improve, as our mathematics advances, as our understanding deepens, we perceive ever larger realities. The universe appears to unfold before us, revealing new scales of existence previously unimagined. Tonight, as your breathing slows and your mind opens to these ideas, we will travel together across this cascade of magnitudes. We will stand on mountains and drift through galaxies. We will try to comprehend structures so vast that light takes billions of years to cross them. And perhaps, in exploring what is biggest, we might also discover something about ourselves, about our capacity for wonder, about our ability to comprehend that which we can never directly experience, about our place in this unfathomable cosmos. So close your eyes or leave them open to stare at the darkness. Either way, prepare to journey beyond the familiar scales of everyday life, beyond the sizes and distances that feel intuitive, into realms where numbers become poetry and scale becomes a meditation. What is the biggest thing in the universe? The answer may surprise you, it may humble you, it may even change how you see yourself when morning comes. Let us begin our journey. We live in a world where mountains feel immense, but even Everest is nothing on the cosmic map. Let us begin with ourselves. The human body This vessel you inhabit stands on average between 1.5 to 2 meters tall. Your skin, if unwrapped and laid flat, would cover nearly 2 square meters. Within your skull resides a brain weighing about 1.5 kilograms, containing nearly 86 billion neurons, each forming thousands of connections. Your heart, roughly the size of your clenched fist, beats 70 times per minute, over 100,000 times per day, pushing blood through nearly 100,000 kilometers of vessels. These numbers define our physical existence, yet we rarely think of ourselves in such terms. We experience our bodies not as collections of measurements, but as the primary interface through which we sense the world. Our size becomes our baseline, our internal ruler against which all other scales are measured. Stand beside a tree. A mature oak might reach 20 to 30 meters tall, dwarfing you with its sprawling canopy. The tallest trees on Earth, the coastal redwoods of California, soar to heights of over 100 meters, their uppermost branches disappearing into the mist. That is 50 times the height of a human. Yet we can still comprehend this scale. We can still stand at the base of such a giant and visually trace its trunk skyward, understanding its magnitude through direct experience. Now, consider larger terrestrial structures. The tallest human-made building, the Burj Khalifa in Dubai, rises 830 meters into the sky. This is over 400 times the height of a human being. Yet even this massive structure occupies only a tiny fraction of our planet's surface. Let us climb higher. Mount Everest, the tallest mountain on Earth, stands at 8,848 meters above sea level. Its mass is almost incomprehensible on a human scale, millions of times greater than our bodies. From its peak, one can see the curvature of the Earth, a gentle reminder that even this behemoth exists on something far larger. The true giants of our planet are not solid at all, but liquid. The Pacific Ocean covers 165 million square kilometers, nearly 1/3 of Earth's surface. Its average depth exceeds 4,000 meters, with its deepest point, the Challenger Deep, in the Mariana Trench, plunging to nearly 11,000 meters below sea level. That single trench could swallow Mount Everest with room to spare. How do we comprehend such vastness? We break it into familiar units. We say the Pacific contains over 660 quadrillion liters of water. But what does that mean? Perhaps it is more relatable to say that if you drank 1 liter of seawater each second, it would take you over 21 million years to empty the Pacific. Such is the challenge of grasping large numbers, large volumes, large masses. We must translate them into experiences or timeframes we can intuitively understand. Our planet itself, this Earth beneath your feet right now, has a diameter of approximately 12,742 kilometers. This single number exceeds the distance most humans will travel in their lifetimes. Earth's surface area spans 510 million square kilometers. Its mass, approximately 5.9, 7 times 10 to the 24 kilograms, is so enormous that it creates the gravitational field holding you in place as you listen to these words. Yet our perception of Earth's size is limited by our position upon it. Standing on its surface, we cannot see its curvature without climbing to great heights or venturing to sea. The horizon extends only a few kilometers in any direction. We experience our planet not as a finite sphere, but as an apparently endless plane, stretching to the limits of vision. This limitation of perception defines our relationship with scale. We struggle to truly comprehend sizes beyond what we can directly observe. We can state that light travels at nearly 300,000 kilometers per second, but can we truly grasp what this means? That in the time it takes to blink, light could circle our entire planet 7 times. Scale becomes even more challenging when we consider time. The average human lifespan spans only about 4,000 weeks. Earth has existed for over 4.5 billion years. The ratio between these durations is similar to the ratio between 1 second and 30 years. Our entire lives occupy but a moment in our planet's long history. As we prepare to venture beyond Earth, to explore ever larger structures in our solar system and beyond, it is worth pausing to acknowledge this fundamental tension in our understanding of scale. We perceive the world through human senses, with human brains evolved to comprehend human-sized problems. Yet, we live in a universe where the truly massive exists beyond our direct experience. This is both our limitation and our wonder. We cannot stand beside a star or hold a galaxy in our hands. we will never directly perceive the largest structures in the universe. Yet through observation, through mathematics, through imagination, we extend our comprehension beyond our physical limitations. We reach with our minds where our bodies cannot go. So as you rest there, occupying your human-scaled space, breathing at your human-scaled pace, remember that your consciousness is about to expand far beyond these boundaries. Your imagination will soon travel distances that light itself takes millions of years to cross. Your thoughts will encompass structures so vast that they challenge our very conception of what a thing can be. We live in a world where mountains feel immense, but even Everest is nothing on the cosmic map. Let us now leave our terrestrial home and venture outward to explore the true giants that await us in the depths of space. Beyond the solar system, planets grow stranger and far more massive. As we leave Earth behind, we enter a realm where familiar references begin to fail us. Our planetary home, with its 12,742-kilometer diameter, has been our measure of enormity. But in the wider solar system, Earth is merely a middle-sized world, dwarfed by the true giants that orbit our Sun. Let us first visit Venus, our nearest planetary neighbor. Similar in size to Earth at 12,104 kilometers in diameter, Venus presents a world of extremes. Its crushing atmosphere exerts pressures 92 times greater than Earth's at sea level. Surface temperatures reach 462 degrees Celsius, hot enough to melt lead. Though comparable to our world in scale, Venus demonstrates how planetary conditions can vary dramatically even at familiar sizes. Moving outward, we encounter Mars, our rusty neighbor. Though smaller than Earth at 6,779 kilometers in diameter, Mars still presents a formidable mass. Its volume could contain multiple Mount Everests, multiple Pacific Oceans. Standing on its surface, you would experience a horizon much like Earth's, curving away at a distance that seems to match terrestrial experience. The scale remains comprehensible to our human perspective. The asteroid belt separates the inner rocky worlds from the outer giants. Here, countless rocky bodies orbit the Sun. The largest, Ceres, spans 940 kilometers across, large enough to have rounded under its own gravity. Yet Ceres would fit comfortably within the continental United States, making it tiny compared to what lies beyond. As we journey further outward, we encounter the first true giants of our solar system. Jupiter, the fifth planet from the Sun, redefines our understanding of planetary scale. Its diameter stretches 142,984 kilometers, 11 times wider than Earth. This single measurement fails to convey Jupiter's true enormity. Consider instead that you could fit 1,300 Earths inside Jupiter's volume. If Earth were a grape, Jupiter would be a beach ball. Jupiter's mass, too, defies easy comprehension. At 1.89 times 10 to the 27 kilograms, it contains more than twice the mass of all other planets in our solar system combined. Its gravitational pull is so intense that it noticeably affects the orbits of other planets and has been described as a cosmic vacuum cleaner, capturing comets and asteroids that venture too close. The famous Great Red Spot on Jupiter's surface, a storm that has raged for centuries, spans 16,000 kilometers in width. This single atmospheric feature could comfortably contain our entire planet with room to spare. Imagine a storm so vast that the world you stand upon now could be swallowed within its churning clouds. Jupiter's immense gravitational influence extends far beyond its visible surface. It hosts at least 79 moons, the largest of which are worlds in their own right. Ganymede, Jupiter's largest moon, exceeds even the planet Mercury in size. With a diameter of 5,268 kilometers, this single moon would appear as a substantial planet if it orbited the Sun directly. The Jovian system, Jupiter and its many moons, presents a microcosm of our solar system. The four largest moons, discovered by Galileo in 1610, orbit their parent planet just as the planets orbit the Sun. Their orbital dance, locked in perfect resonance, demonstrates the same gravitational principles that govern the movement of planets. In Jupiter's shadow, we glimpse something of our own world's relationship to our star. Continuing outward, we reach Saturn, perhaps the most visually striking of our solar system's worlds. While slightly smaller than Jupiter, at 120,536 kilometers in diameter, Saturn's most distinctive feature extends its apparent size dramatically. Its rings span more than 270,000 kilometers from edge to edge, yet they are remarkably thin, in most places less than 10 meters thick. If scaled down to the size of a sheet of paper, the rings would be 1,000 kilometers wide, but thinner than a razor's edge. Saturn's density presents another curiosity. At 0.687 grams per cubic centimeter, this enormous planet is less dense than water. Placed in a hypothetical ocean large enough to contain it, Saturn would float. Yet despite this relatively low density, Saturn's total mass reaches 5.68 times 10 to the 26 kilograms, making it the second most massive planet in our solar system. Like Jupiter, Saturn hosts a family of moons, 62 at current count. Its largest, Titan, is the only moon in our solar system with a substantial atmosphere, thicker even than Earth's. This moon, larger than the planet Mercury, represents yet another scale of world within the realm of planets, a reminder that size exists on a continuum rather than in discrete categories. Moving still further from the Sun, we encounter the ice giants, Uranus and Neptune. Similar in size to one another, these worlds still dwarf our Earth. Uranus, with a diameter of 51,118 kilometers, could contain 64 Earths within its volume. Neptune, slightly smaller at 49,528 kilometers in diameter, could hold 57 Earths. These ice giants, composed primarily of water, ammonia, and methane ices surrounding small rocky cores, represent a planetary scale beyond our everyday experience. Uranus presents a unique feature in our solar system, an axial tilt of 97 degrees. This means the planet essentially rotates on its side, with its poles facing toward and away from the Sun at different points in its orbit. A year on Uranus lasts 84 Earth years, meaning each pole experiences 42 years of continuous daylight followed by 42 years of darkness. Imagine a world so vast that its seasons unfold over decades, where a single summer might span a human lifetime. Neptune, the furthest known planet from our Sun, experiences the most extreme weather in the solar system. Winds race around its upper atmosphere at speeds exceeding 2,160 kilometers per hour, faster than the speed of sound on Earth. The energy driving these winds remains mysterious, as Neptune receives only 1/900th the sunlight that reaches Earth. Something within this distant giant generates enormous energy, creating storms that would engulf our entire planet. Beyond Neptune lies the dwarf planet Pluto and the vast Kuiper Belt, a region populated by ice-rich objects orbiting at the solar system's edge. While fascinating, these distant worlds pale in size compared to the giants we have already encountered. They represent not an increase in scale, but a transition zone between our solar system and the greater cosmos beyond. Yet even these giants of our solar system are modest compared to what astronomers have discovered orbiting other stars. The exoplanet HD 100546b, orbiting a star 1,300 light-years away, has an estimated diameter of 570,000 kilometers, roughly 4 times larger than Jupiter. If placed in our solar system, this world would extend nearly to the orbit of Mars. The planet T-Res 3b, located about 690 light-years from Earth, has a mass approximately twice that of Jupiter, but is compressed to a slightly smaller size due to its proximity to its star. This hot Jupiter orbits its star at a distance of only 3.1 million kilometers, less than 10 times the diameter of the star itself. At this distance, the planet completes an orbit in just 31 hours and reaches temperatures of nearly 1,700 degrees Celsius. Such extreme conditions create weather unlike anything in our solar system, with silicate minerals raining from clouds and supersonic winds racing around the planet. Another remarkable exoplanet, WASP-76b, discovered in 2016, orbits so close to its star that its dayside temperatures reach 2,200 degrees Celsius, hot enough to vaporize iron. This creates a unique meteorological phenomenon, iron rain. Gaseous iron in the atmosphere condenses into liquid droplets on the cooler night side of the planet, falling as metallic precipitation before vaporizing again when cycled back to the day side. Another class of objects blurs the boundary between planets and stars. Brown dwarfs, often called failed stars, lack the mass to sustain hydrogen fusion in their cores, but grow far larger than any planet. The brown dwarf Y0855 plus 0714, discovered in 2013, has a diameter roughly 100,000 kilometers. What makes this object remarkable is not just its size, but its mass, 80 times greater than Jupiter's. Its gravitational pull creates pressures and temperatures that approach those needed for nuclear fusion, the process that powers stars. Then there are the super-Jupiters, exoplanets, with masses many times that of our own gas giant. HD 180599b, located 400 light-years from Earth, has a mass approximately 14 times that of Jupiter. Its immense gravitational field creates atmospheric pressures that likely compress hydrogen into exotic metallic states, where the gas behaves more like a liquid metal than the hydrogen we know on Earth. Some of these distant worlds orbit so close to their parent stars that their atmospheres are being continuously stripped away by stellar radiation. The planet HD 20945-8b, 215 light-years from Earth, loses an estimated 8,000 tons of its gaseous envelope every second, creating a comet-like tail that stretches millions of kilometers into space. Our journey through planetary scale reveals an important truth about the universe. At each level of magnitude, new physical processes become dominant. Earth-sized worlds are shaped primarily by geological forces, plate tectonics, and relatively thin atmospheres. Jupiter-sized planets are dominated by fluid dynamics, powerful magnetic fields, and self-compression due to gravity. And the largest planetary bodies approach the conditions found in stars, with cores so hot and compressed that they begin to blur the distinctions between states of matter. As we prepare to leave the realm of planets behind, it's worth reflecting on how our perspective has already expanded. The Earth beneath your feet, once your entire world, now appears as a modest sphere among giants. Jupiter, which appears as nothing more than a bright point of light in our night sky, has revealed itself as a world of almost unimaginable proportions. And beyond our solar system, planets grow stranger and far more massive. Yet we have only begun our journey of scale. Beyond the realm of planets lie objects so large that planets become mere specks in comparison. Gas giants may impress us with their enormity. Brown dwarfs may blur the line between planet and star. But as we are about to discover, even Jupiter, even the super-Jupiters and brown dwarfs, are infinitesimal compared to the true leviathans of the cosmos. To find them, we must look to the stars themselves. Stars can grow hundreds of times wider than our Sunday, but they are not the biggest the universe builds. As we leave behind the realm of planets, we enter a domain where scale takes another dramatic leap. Our Sunday, that brilliant yellow star that has nurtured life on Earth for billions of years, serves as our new reference point. With a diameter of 1,390,000 kilometers, the Sun could contain 1,300,000 Earths within its volume. Light takes 4.5 seconds just to travel from one side of the Sun to the other. Every second, it converts 600 million tons of hydrogen into helium, releasing energy equivalent to 92 billion megatons of TNT. These numbers already strain our comprehension, yet our Sunday is merely average among stars, a middleweight in the cosmic arena. To truly understand stellar scale, we must explore both the smallest and largest stars, spanning a range that dwarfs the variation we saw among planets. At the lower end of the stellar spectrum, we find red dwarfs like Proxima Centauri, our nearest stellar neighbor beyond the Sun. With a diameter just 1/7 that of our Sunday, Proxima Centauri is barely larger than Jupiter, though far more massive. Despite its small size, it still qualifies as a true star, fusing hydrogen into helium within its core, a process that will continue for trillions of years, long after our Sunday has exhausted its fuel. Even smaller are the white dwarfs, the remnant cores of stars like our Sunday that have shed their outer layers at the end of their lives. A typical white dwarf measures about 15,000 kilometers across, similar in size to Earth, yet contains half the mass of our Sunday compressed into this tiny volume. A sugar cube-sized piece of white dwarf material would weigh approximately 1 ton on Earth. These stellar corpses represent matter compressed to densities nearly unimaginable in our everyday experience. Moving upward in scale, we encounter stars like Alpha Centauri A, slightly larger than our Sunday at 1.7 times its diameter. Then come the subgiants and giants, stars that have evolved beyond their stable middle age and begun to expand. Pollux, the brightest star in the constellation Gemini, has swollen to about 9 times the diameter of our Sunday, large enough to engulf the inner planets if placed at the center of our solar system. But these stars are merely the prelude to the true giants of the stellar realm. Aldebaran, the orange eye of Taurus the Bull, spans 44 times the diameter of our Sunday. If centered in our solar system, its surface would extend roughly to Mercury's orbit. Arcturus, a red giant visible in Earth's northern sky, extends 26 times wider than our Sunday. These stars, though far more massive than our Sunday, have much lower densities. Their matter spread across vastly larger volumes, as their outer layers expand during the late stages of stellar evolution. As impressive as these giants are, they pale in comparison to the supergiant stars. Betelgeuse, the distinctly reddish star marking the shoulder of Orion, measures approximately 1,000 times the diameter of our Sunday. If placed at the center of our solar system, its surface would extend beyond the orbit of Jupiter, engulfing the 4 terrestrial planets, the asteroid belt, and the solar system's largest planet in one swoop. Light would take 7 hours to cross its diameter. Despite its enormous size, Betelgeuse contains only about 20 times the mass of our Sun. Its matter has expanded to such an extent that its average density is less than 1/1,000,000th that of our Sun, making it more rarefied than many artificial vacuums created on Earth. If Betelgeuse were hollowed out, it could contain nearly 1 billion suns within its volume. Yet even Betelgeuse is not the largest known star. That distinction belongs to stars like UY Scuti, a red hypergiant located about 9,500 light-years from Earth in the constellation Scutum. With a radius estimated at 755 times that of our Sun, UY Scuti would extend nearly to the orbit of Saturn if placed at the center of our solar system. Its diameter spans approximately 1.6 billion kilometers, a distance so vast that light takes nearly 1.5 hours to cross it. Imagine a sphere so large that even at the speed of light, you would need to travel for 90 minutes just to reach the opposite side. Such scales transcend our everyday experience of size and distance, requiring us to adopt new frameworks of understanding. Another stellar behemoth, VY Canis Majoris, located about 3,900 light-years from Earth, in the constellation Canis Major, has a radius approximately 1,500 times that of our Sun. Its volume could contain nearly 9 billion suns. If Earth were a grain of sand, VY Canis Majoris would be a sphere nearly 1 kilometer in diameter. The existence of such enormous stars raises intriguing questions about the limits of stellar size. Why don't stars grow even larger? The answer lies in the physics of stellar structure. As a star's mass increases, so does the gravitational force compressing its core, raising the internal temperature and pressure. This accelerates the rate of nuclear fusion, causing the star to burn through its fuel supply at an exponentially faster rate. UY Scuti, despite its enormous size, is only about 30 times more massive than our Sun. Its great volume results from its expanded outer layers, puffed up as the star approaches the end of its life. This tenuous envelope will eventually be shed, leaving behind a much smaller stellar remnant. The most massive stars known, such as R136, a one in the Large Magellanic Cloud, contain more than 300 times the Sun's mass, but are much smaller in diameter than stars, like UY Scuti. A star's luminosity increases dramatically with mass. R136A1, with its 300 solar masses, shines with the light of 8 million suns. It will exhaust its nuclear fuel in just a few million years, compared to the 10 billion-year lifespan of our Sun. In the cosmos, greater size often comes at the cost of longevity. The largest stars are cosmic sparklers, brilliant but brief. The physical processes that shape these stellar giants differ from those operating in smaller stars. In our Sun, energy generated in the core through hydrogen fusion must travel outward through successive layers of increasingly less dense plasma. This energy transport occurs primarily through radiation in the interior and convection near the surface. But in supergiant stars, convection can dominate throughout much of the star's volume, creating enormous cells of rising and falling plasma that dwarf our Sun in size. These convective processes create the distinctive mottled appearance of stars like Betelgeuse, whose surface features have been directly imaged by powerful telescopes. Rather than appearing as a smooth, uniform disk, Betelgeuse reveals enormous bright and dark patches, regions where hot plasma rises to the surface, or cooler material sinks inward. A single one of these convective cells on Betelgeuse could engulf our entire Sunday. The largest stars also experience substantial mass loss, shedding material through powerful stellar winds. Betelgeuse loses approximately 1 Earth mass of material every year, creating an extended nebula of dust and gas that stretches hundreds of times beyond the visible surface of the star. Eventually, this mass loss will transform the star, stripping away its outer layers until only the hot, dense core remains. The ultimate fate of these stellar giants adds another dimension to our understanding of cosmic scale. Stars like Betelgeuse and UY Scuti will end their lives in spectacular supernova explosions, briefly outshining entire galaxies before collapsing into neutron stars or black holes. A neutron star, though only about 20 kilometers in diameter, contains more mass than our Sun compressed to densities where a teaspoon of material would weigh billions of tons on Earth. Black holes represent an even more extreme state of matter, where a star's mass has collapsed to a point of infinite density, creating a region of space from which nothing, not even light, can escape. The event horizon of a stellar mass black hole, typically tens of kilometers across, marks the boundary of this cosmic abyss. Despite their compact size, black holes warp the very fabric of space and time around them, bending light and altering the paths of nearby objects. At the centers of most large galaxies lurk supermassive black holes, with masses millions or billions of times that of our Sun. The black hole at the center of our Milky Way, Sagittarius A star, contains about 4 million solar masses. Despite this enormous mass, its event horizon spans just 17 times the diameter of our Sun, demonstrating how black holes represent the ultimate compression of matter. As we reflect on stellar scale, several patterns emerge. Stars span an enormous range of sizes, from white dwarfs barely larger than Earth to hypergiants that could engulf much of our solar system. Yet stellar size correlates imperfectly with stellar mass. The largest stars by diameter, like UY Scuti, contain only a few dozen solar masses, while the most massive stars known, like R13601, pack hundreds of solar masses into much smaller volumes. This discrepancy arises from the different stages of stellar evolution. Main sequence stars like our Sun maintain a relatively compact size through the balance of gravitational compression and the outward pressure generated by nuclear fusion. As stars age and exhaust the hydrogen in their cores, they expand dramatically, becoming red giants or supergiants, with much larger diameters but similar masses to their main sequence selves. The relationship between size and temperature also reveals interesting patterns. The largest stars tend to be among the coolest, with surface temperatures around 3,000 degrees Celsius. In contrast, the hottest stars, with surfaces reaching 50,000 degrees Celsius, tend to be much smaller in diameter, though often more massive. Our Sun, with a surface temperature of about 5,500 degrees Celsius, falls between these extremes. As we prepare to leave the realm of individual stars behind, it's worth pondering the scale of our journey so far. We began with the human perspective, measuring objects in meters. We expanded to planetary scales, where diameters are measured in thousands or hundreds of thousands of kilometers. Now, we've explored stellar scales, where objects span millions or billions of kilometers. Each increase in scale has revealed new physical processes, new forms of organization, new wonders. Yet the cosmos has more to show us. As vast as stars like UY Scuti and VY Canis Majoris are, they represent merely the building blocks of even larger structures. When stars gather by the thousands, the millions, the billions, they create collectives whose scale dwarfs even the stellar giants we've explored. Stars can grow hundreds of times wider than our Sun, but they are not the biggest things the universe builds. To find those, we must zoom out once more, to the gathering places of stars, the stellar cities we call star clusters. Clusters light the darkness like cosmic lanterns, but they are only the beginning. As we continue our journey outward in scale, we move from individual stars to their natural gatherings. Stars rarely form in isolation. Instead, they emerge in groups from the same vast clouds of gas and dust, born as siblings from a common nursery. These stellar families, bound together by mutual gravitational attraction, form structures known as star clusters. The night sky reveals numerous examples visible to the naked eye. Perhaps the most famous is the Pleiades, also known as the Seven Sisters, a grouping of stars in the constellation Taurus. To our unaided eyes, this cluster appears as a tight knot of 6 or 7 stars. Through binoculars or a small telescope, however, hundreds of stars reveal themselves, all moving together through space as a single unit. The Pleiades spans about 13 light-years in diameter. Light, traveling at nearly 300,000 kilometers per second, would take 13 years to cross from one side of this cluster to the other. Within this volume, the cluster contains over 1,000 stars, most of them young, hot and blue, having formed together a mere 100 million years ago, recent by cosmic standards. For perspective, recall that our entire solar system, from the Sun to the orbit of Neptune, spans just 9 light-hours in diameter. The Pleiades cluster could contain over 12,000 solar systems arranged side by side. Yet in cosmic terms, the Pleiades represents a relatively modest star cluster, both in terms of size and stellar population. Star clusters come in 2 main varieties, each with distinctive characteristics and origins. Open clusters like the Pleiades form relatively recently in the spiral arms of galaxies. They contain anywhere from dozens to a few thousand stars, spanning volumes typically between 5 and 30 light-years across. These clusters are loosely bound by gravity, their stars separated by distances averaging a few light-years. Over time, open clusters gradually disperse as they orbit through their host galaxy, their stars pulled away by gravitational interactions with other clusters, molecular clouds, and the galaxy itself. Our Sun likely formed within such a cluster roughly 4.5 billion years ago. Its stellar siblings have long since dispersed throughout the Milky Way, making it impossible to identify our Sun's birth cluster. Some stars currently near our Sun may be distant relatives, sharing a common origin but now moving along independent paths. Far more impressive in scale are globular clusters, ancient stellar metropolises that orbit most large galaxies. These spherical collections contain hundreds of thousands to millions of stars, packed into volumes typically spanning 100 to 200 light-years in diameter. The stars within globular clusters are among the oldest in the universe, having formed 10 to 13 billion years ago, not long after the Big Bang itself. Omega Centauri, the largest globular cluster in our Milky Way, spans about 170 light-years across and contains approximately 10 million stars. The density of stars near its core is so great that they are separated by an average distance of just 1/3 of a light-year, less than 1/10 the distance from our Sun to its nearest stellar neighbor. If Earth orbited a star near the center of Omega Centauri, our night sky would blaze with thousands of stars brighter than Sirius appears from Earth. The combined light of these stars would banish true darkness, creating a perpetual twilight, even in the absence of the host star. Imagine standing on a planet within such a cluster. In every direction, stars would crowd the sky, not as distant points of light, but as discernible disks. Multiple shadows would stretch from every object, cast by dozens of nearby suns. The concept of night would have no meaning for any civilizations that might evolve in such an environment. Despite containing millions of stars, globular clusters are remarkably stable structures. Their extreme age testifies to this stability. Messier 13, a globular cluster in the constellation Hercules, has maintained its spherical form for over 11 billion years as it orbits the Milky Way. Its stars move through the cluster like bees around a hive, each following a complex trajectory under the influence of the cluster's combined gravitational field. The mass of a typical globular cluster ranges from 100,000 to several million times the mass of our Sun. This enormous mass generates a substantial gravitational field, binding the cluster together, despite the disruptive forces it encounters during its orbit around the galaxy. Globular clusters typically follow elongated elliptical paths that take them far above and below the galactic plane, spending most of their time in the galactic halo, the spherical region surrounding the galaxy's disk. The largest known globular cluster, R136 in the Large Magellanic Cloud, spans nearly 200 light-years and contains tens of millions of stars. Near its center, the stellar density reaches an astonishing 100,000 stars per cubic light-year. This extreme environment fosters unusual stellar interactions. Stars that would normally never encounter another star in their entire lifetimes might experience dozens of close passes in a globular cluster, sometimes resulting in stellar collisions or the formation of binary systems. These dense stellar environments also accelerate the evolution of exotic objects. Globular clusters contain unusually high populations of pulsars, neutron stars that emit beams of radiation as they spin, as well as black holes and blue stragglers, stars that appear younger than they should be, likely the result of stellar mergers. Between the extremes of open and globular clusters lie intermediate clusters, sharing characteristics of both. The Hyades, the closest star cluster to our solar system, at just 153 light-years away, represents this intermediate type. Spanning about 15 light-years in diameter and containing several hundred stars, the Hyades forms the distinctive V shape that marks the face of Taurus, the bull, in our night sky. Young, massive clusters represent another variant, containing tens of thousands of stars within volumes similar to open clusters. The most spectacular example is R136 at the center of the Tarantula Nebula in the Large Magellanic Cloud. This cluster packs over 10,000 massive stars, including many of the most massive known, into a region just a few light-years across. The combined energy output of these stars creates vast bubbles of hot gas, driving complex flows of matter and energy that influence star formation across thousands of light-years. Some clusters exist within vast clouds of gas and dust called nebulae, stellar nurseries, where new stars continue to form. The Orion Nebula, visible to the naked eye as a fuzzy patch in the Sword of Orion, contains a young cluster with over 3,000 stars. This nebula spans approximately 24 light-years and contains enough gas to form thousands more stars. When we look at the Orion Nebula, we witness stellar birth in progress, a process that has continued throughout cosmic history. Star clusters serve several important functions in galactic ecosystems. They act as gravitational anchors, their combined mass influencing the motion of gas clouds and individual stars. They serve as natural laboratories for studying stellar evolution, since all stars in a cluster formed at roughly the same time, from the same material, allowing astronomers to observe how stars of different masses develop over time. And they function as factories for exotic stellar objects, their dense environments fostering interactions that create neutron stars, black holes, and unusual binary systems. The organization of clusters themselves reveals patterns at even larger scales. Open clusters tend to align with spiral arms in galaxies like our Milky Way, tracing the regions of active star formation. Globular clusters form spherical distributions around galactic centers, their orbits carrying them through the galactic halo. These patterns reflect the different formation, histories, and ages of the two cluster types. As we expand our view further, we find that clusters themselves cluster. The Hyades and Pleiades clusters form part of a larger association of stars and clusters called the Taurus-Scorpius Association. This association spans several hundred light-years and formed from a single enormous cloud of gas and dust. Such stellar associations represent an intermediate scale between individual clusters and the spiral arms of galaxies. In some regions of the universe, clusters merge to form superclusters, not to be confused with the galactic superclusters we will explore later. NGC 6052, located about 5,000 light-years from Earth, in the constellation Scorpius, appears to be such a merged cluster containing multiple distinct populations of stars with different ages. Its total mass exceeds 30,000 solar masses, and it spans roughly 70 light-years. As impressive as these clusters are, perspective is important. Even Omega Centauri, with its millions of stars and span of 170 light-years, represents just a tiny fraction of its host galaxy. The Milky Way contains at least 150 globular clusters, orbiting at distances up to 100,000 light-years from the galactic center. These clusters, impressive structures in their own right, serve as satellites to the far larger galactic system. What determines the upper size limit for star clusters? Several factors come into play. As clusters grow larger, the gravitational forces binding them become less uniform, making them increasingly vulnerable to disruption. Larger clusters also require more massive gas clouds for their formation, and such clouds become increasingly rare beyond certain scales. Finally, feedback from the first stars to form in a cluster, particularly the intense radiation and stellar winds from massive stars, can disperse the remaining gas cloud before it can form additional stars, limiting the cluster's growth. Despite these limitations, the universe has had nearly 14 billion years to experiment with different clustering patterns. In regions where galaxies collide, the resulting gravitational disturbances can compress enormous volumes of gas, potentially forming superstar clusters that dwarf anything in our relatively quiet Milky Way. In the early universe, when gas clouds were both more massive and more pristine, even larger clusters may have formed. As we prepare to leave the realm of star clusters behind, it's worth reflecting on the progression of scale in our journey. We began with human dimensions, measuring objects in meters. We expanded to planetary scales, where objects span thousands to hundreds of thousands of kilometers. We explored stellar scales, with objects measuring millions to billions of kilometers across. Now, with star clusters, we've entered a domain where objects span multiple light years, distances so vast that light itself, moving at 300,000 kilometers per second, takes years to cross them. Yet even the largest globular clusters, spanning hundreds of light years and containing millions of stars, represent merely the building blocks of the next level in our cosmic hierarchy. When we step back and observe the gathering of not just stars but star clusters, when we expand our view to encompass volumes thousands of light years across, we encounter the next tier of cosmic structure: galaxies, the island universes that house all the stars, clusters, and nebulae we've explored thus far. Clusters light the darkness like cosmic lanterns, but they are only the beginning. To continue our journey of scale, we must expand our vision once more, to encompass the vast stellar cities we call galaxies. Each galaxy is a city of stars, but galaxies do not live alone. As we expand our view beyond star clusters, we encounter structures of such immensity that they redefine our understanding of cosmic scale. Galaxies, vast collections of stars, gas, dust, and dark matter, represent the next fundamental level in the hierarchy of cosmic structures. Our own Milky Way galaxy, home to our Sun and everything familiar to human experience, serves as our first reference point for understanding these stellar metropolises. The Milky Way spans approximately 100,000 light-years from edge to edge. Light, traveling at 300,000 kilometers per second, requires 100,000 years to cross this distance. For comparison, modern human civilization has existed for only about 10,000 years. The entirety of recorded human history represents just a tenth of the time it takes light to traverse our galaxy. Within this vast expanse, the Milky Way contains between 200 billion and 400 billion stars. If you could count these stars at a rate of 1 per second, the task would require over 10,000 years to complete. Each of these stars represents a sun, many with their own planetary systems. The potential number of worlds within our galaxy alone stretches into the trillions. Our galaxy forms a spiral pattern, with arms of stars, gas, and dust winding outward from a central bulge. This spiral structure spans 3 dimensions, forming a disk roughly 1,000 light-years thick in most regions. Our Sun resides in a minor spiral arm called the Orion Arm, about 26,000 light-years from the galactic center. From our position, the galaxy appears as a faint band of light stretching across the night sky, the source of our galaxy's name. The Milky Way's disk rotates, with stars near our Sun's position moving at about 220 kilometers per second relative to the galactic center. Despite this incredible speed, the immense size of the galaxy means that our Sun requires about 230 million years to complete a single orbit. Since its formation 4.5 billion years ago, our Sun has completed only about 20 galactic years. Surrounding the disk, a spherical halo extends outward for at least 150,000 light-years, containing globular clusters, individual stars, and vast amounts of dark matter. This invisible component reveals itself only through its gravitational effects. Scientists estimate that dark matter comprises approximately 85% of the Milky Way's total mass, forming a vast spherical structure that dwarfs the visible galaxy. At the center of the Milky Way lies a supermassive black hole named Sagittarius A star, containing the mass of approximately 4 million suns compressed into a region smaller than our solar system. This black hole, though massive by stellar standards, contributes only a tiny fraction of the galaxy's total mass. Its primary significance lies in its role as the gravitational anchor at the heart of our galactic system. As impressive as the Milky Way appears, it represents just one of trillions of galaxies in the observable universe. Galaxies come in a variety of shapes and sizes, each with distinctive characteristics that reflect their formation, history, and environmental context. Spiral galaxies like our Milky Way feature prominent disk structures with arms winding outward from a central bulge. The Andromeda Galaxy, also known as Messier 31, represents our nearest large spiral neighbor at approximately 2.5 million light-years from Earth. Slightly larger than the Milky Way, at 220,000 light-years in diameter, Andromeda contains roughly 1 trillion stars. Its spiral arms, viewed from Earth at an angle of about 16 degrees, create a distinctive elliptical appearance in our night sky. The spiral pattern itself represents a density wave, a region where stars and gas clouds temporarily concentrate as they orbit the galactic center. This concentration triggers new star formation, creating the bright blue patches visible along spiral arms. The youngest, most massive stars shine with intense blue light, highlighting these regions of active stellar birth. Older, redder stars distribute more evenly throughout the galactic disk. Not all spiral galaxies display the same structure. Some, like NGC 1300 in the constellation Eridanus, feature a prominent central bar from which the spiral arms emerge. Our Milky Way belongs to this barred spiral category, with a central bar spanning about 27,000 light-years. Approximately 2/3 of spiral galaxies feature these bar structures, which channel gas toward the galactic center and influence star formation patterns throughout the disk. Moving to a different galaxy type, elliptical galaxies lack the distinctive disk and spiral structure of galaxies like the Milky Way. Instead, they form roughly ellipsoidal or spherical shapes, with stars moving in random orbits, rather than the organized rotation seen in spiral galaxy disks. The largest known galaxies in the universe fall into this elliptical category. Messier 87, also known as Virgo A, represents a typical giant elliptical galaxy. Located approximately 54 million light-years from Earth in the Virgo cluster, this galaxy spans about 120,000 light-years and contains several trillion stars. Unlike spiral galaxies, elliptical galaxies appear yellow or red in color, indicating older stellar populations and minimal ongoing star formation. The true giants among galaxies are the supergiant ellipticals, enormous structures typically found at the centers of galaxy clusters. IC 1101, the largest known galaxy, resides at the center of the Abell 2029 galaxy cluster, approximately 1.07 billion light-years from Earth. This behemoth spans approximately 5.5 million light-years in diameter, nearly 50 times wider than the Milky Way. If placed where the Milky Way is, IC 1101 would engulf our local group of galaxies and extend far beyond. The mass of IC 1101 exceeds 100 trillion solar masses, with a stellar population estimated at 100 trillion stars. Such galaxies likely form through the merger of multiple smaller galaxies, a process that continues today throughout the universe. These galactic collisions, occurring over hundreds of millions of years, reshape the participating galaxies and trigger bursts of intense star formation. In contrast to these giants, dwarf galaxies represent the smallest end of the galactic spectrum. The Milky Way hosts several dozen satellite dwarf galaxies, including the large and small Magellanic Clouds, visible from Earth's southern hemisphere. These diminutive galaxies typically span just a few thousand light-years and contain millions to billions of stars. The Segway 1 dwarf galaxy, one of the smallest known, contains only about 1,000 stars, within a diameter of approximately 600 light-years, smaller than many globular clusters. Between these extremes lie numerous variations. Lenticular galaxies combine characteristics of both spiral and elliptical types, featuring a disk structure without spiral arms. Irregular galaxies like the Large Magellanic Cloud lack defined structure, often due to gravitational interactions with larger neighbors. Ring galaxies such as Hoag's Object Display, striking circular structures formed through complex gravitational interactions between colliding galaxies. The space between galaxies deserves attention as well. While often portrayed as empty, intergalactic space contains diffuse gas, isolated stars ejected from their home galaxies, and potentially vast amounts of dark matter. This material, though tenuous by terrestrial standards, accounts for a significant fraction of the universe's total ordinary matter. Galaxies themselves distribute unevenly throughout space. Rather than spreading uniformly, they gather into groups, clusters, and even larger structures, creating a cosmic web that spans the observable universe. Our Milky Way participates in a small collection called the Local Group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and more than 50 dwarf galaxies within a volume spanning approximately 10 million light-years. Within galaxies, matter concentrates to densities trillions of times greater than the cosmic average. Yet even these concentrations represent what astronomers would consider a vacuum. by laboratory standards. The Milky Way's disk contains an average of approximately 1 atom per cubic centimeter, with densities increasing toward the galactic center and in regions of active star formation. For comparison, Earth's atmosphere at sea level contains roughly 10 to the 19th atoms per cubic centimeter. This sparse distribution means that despite their countless stars, galaxies consist mostly of empty space. When galaxies collide, individual stars rarely impact one another directly. Instead, gravitational interactions and the compression of gas clouds dominate these encounters. Our Milky Way and the Andromeda Galaxy will begin colliding in approximately 4.5 billion years, eventually merging to form a single elliptical galaxy, sometimes called Milkomeda. The colors of galaxies reveal much about their history and current state. Spiral galaxies typically display blue disks and yellowish central bulges, indicating both young, hot stars in the spiral arms and older stellar populations in the central regions. Elliptical galaxies appear predominantly yellow to red, suggesting minimal recent star formation. Some galaxies, called starburst galaxies, glow intensely blue due to massive waves of star formation, triggered by galactic interactions or internal processes. Galaxy distribution reveals important patterns at even larger scales. Studies like the Sloan Digital Sky Survey have mapped hundreds of thousands of galaxies, revealing that they arrange themselves along filaments and sheets surrounding vast, empty regions called voids. This pattern, often described as resembling a cosmic web or a system of bubbles, extends across billions of light years and provides crucial insights into the universe's evolution since the Big Bang. Active galactic nuclei represent another fascinating aspect of galactic scale. In some galaxies, the central supermassive black hole actively consumes surrounding material, creating an accretion disk that heats to millions of degrees. This process generates enormous energy outputs, sometimes producing jets of particles that extend millions of light years into intergalactic space. Quasars, the most extreme examples of this phenomenon, can outshine their entire host galaxies, visible across billions of light years. The relationship between visible matter and dark matter introduces yet another dimension to galactic scale. Observations of galactic rotation rates indicate that dark matter extends far beyond the visible boundaries of galaxies, forming halos that may span millions of light years. The Milky Way's dark matter halo likely extends at least 500,000 light-years from the galactic center, containing perhaps 10 times more mass than all the visible stars, gas, and dust combined. Galaxies evolve over billions of years, transforming from one type to another through internal processes and external interactions. Young galaxies in the early universe appeared smaller, more irregular, and more actively star-forming than typical galaxies today. Over cosmic time, galaxies grow through mergers and accretion of surrounding material, generally evolving from spiral to elliptical forms as they age. This evolution continues today, with our own Milky Way currently absorbing several dwarf galaxies, their stars gradually integrating into our galactic system. The most distant galaxies observed by modern telescopes appear as they existed just a few 100 million years after the Big Bang, when the universe was less than 5% of its current age. These early galaxies differ significantly from those in our cosmic neighborhood, typically appearing smaller, bluer, and more chaotic. Their light has traveled through space for more than 13 billion years before reaching our telescopes, providing a direct view into the universe's distant past. The concept of galactic habitable zones introduces an interesting biological perspective on galactic scale. Just as stars have habitable zones where planetary temperatures might support liquid water, galaxies may have regions more conducive to life. Too close to the galactic center, intense radiation and frequent supernova explosions might sterilize planets. Too far from the center, the scarcity of heavy elements might prevent rocky planets from forming. Our Sun occupies what might be a fortunate middle ground in a relatively quiet neighborhood with sufficient heavy elements for planetary formation. Galactic magnetic fields represent another aspect of scale, often overlooked in discussions of galaxies. The Milky Way generates a magnetic field that spans its entire disk, influencing the movement of charged particles and potentially affecting star formation. These fields, though incredibly weak by terrestrial standards, extend across thousands of light years and play important roles in galactic evolution. The movement of stars within galaxies reveals complex dynamics operating on timescales of billions of years. In spiral galaxies, stars near the center complete their orbits much faster than those in the outer regions, creating a differential rotation that would theoretically wind the spiral arms tighter over time. That this winding doesn't occur suggests that spiral arms represent density waves propagating through the galactic disk rather than fixed collections of specific stars. Within elliptical galaxies, stars move in random directions rather than following circular orbits. This chaotic motion reflects the formation history of these galaxies, typically resulting from the merger of multiple spiral galaxies. During such mergers, the ordered rotational motion of the original galaxies transforms into the random motions characteristic of elliptical systems. The aging of stellar populations creates distinctive patterns across galaxies. Spiral arms appear blue due to the presence of massive, short-lived stars that form continuously within these regions. The spaces between spiral arms contain predominantly older, redder stars. In elliptical galaxies, the absence of gas for new star formation means that the stellar population gradually ages, with the youngest stars being billions of years old. As impressive as individual galaxies appear, they represent just one tier in the cosmic hierarchy of structure. Galaxies themselves gather into larger assemblages, creating patterns that span hundreds of millions of light years. The Virgo cluster, the nearest large galaxy cluster to Earth, contains more than 1,500 galaxies within a volume approximately 10 million light-years in diameter. At its center, enormous elliptical galaxies like Messier 87 dominate, having grown through the cannibalization of smaller galaxies. Beyond these clusters lie even larger structures, superclusters, spanning hundreds of millions of light-years, which we will explore in subsequent chapters. These vast assemblages of galaxy clusters trace the largest coherent structures known in the universe, revealing patterns imprinted during the earliest moments after the Big Bang. As we prepare to leave the realm of individual galaxies behind, it's worth reflecting on the progression of scale in our journey. We began with human dimensions, measuring objects in meters. We expanded to planetary scales, with objects spanning thousands to hundreds of thousands of kilometers. We explored stellar scales, with objects measuring millions to billions of kilometers across. Star clusters introduced us to structures spanning tens to hundreds of light years. Now, with galaxies, we've entered a domain where objects span tens of thousands to millions of light years. Distances so vast that the light we observe from distant galaxies departed before Earth itself had formed. Yet even galaxies, these enormous island universes housing hundreds of billions of stars, represent merely the building blocks of the next level in our cosmic hierarchy. When we observe the gathering of not just stars or star clusters but entire galaxies, when we expand our view to encompass volumes spanning billions of light years, we encounter the next tier of cosmic structure, galaxy clusters, and the larger patterns they form across the observable universe. Each galaxy is a city of stars, but galaxies do not live alone. They gather in clusters, forming communities tied together by mutual gravitational attraction. To continue our journey of scale, we must expand our vision once more to encompass these vast galactic neighborhoods we call galaxy groups and clusters. Galaxies dance together in clusters, pulled by gravity across invisible threads. As we continue our journey outward in scale, we transcend individual galaxies to explore their natural gatherings. Just as stars rarely exist in isolation, preferring the gravitational company of clusters, galaxies too form social structures across the cosmos. These galactic communities, bound by mutual gravitational attraction, create the next tier in our cosmic hierarchy of structure. Our own Milky Way participates in such a gathering, a collection known as the Local Group. This assemblage spans approximately 10 million light-years in diameter and contains more than 50 known galaxies. If the Milky Way represents a cosmic metropolis with hundreds of billions of stellar inhabitants, the Local Group constitutes a province containing dozens of such cities, ranging from the majestic Andromeda Galaxy to tiny dwarf spheroidal galaxies barely visible to our most powerful telescopes. Within the Local Group, 3 spiral galaxies dominate: our Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. The Andromeda Galaxy, the largest member, spans approximately 220,000 light-years in diameter and contains about 1 trillion stars. The Triangulum Galaxy, slightly smaller than our Milky Way, at 60,000 light-years across, contains roughly 40 billion stars. These 3 spiral systems contain approximately 98% of the Local Group's total stellar mass. The remaining members consist primarily of dwarf galaxies, many orbiting the larger spirals as satellites. The Large and Small Magellanic Clouds, visible from Earth's southern hemisphere, represent the most prominent of these Milky Way satellites. Other members include dwarf elliptical, dwarf spheroidal, and irregular galaxies, each containing anywhere from a few million to several billion stars. Despite spanning 10 million light-years, the local group represents a relatively compact and isolated galaxy group. The nearest similar collection, the Sculptor group, lies approximately 11 million light-years from us. Between these groups stretches a relative void, sparsely populated with individual galaxies and smaller associations. The local group itself forms part of a larger structure called the Virgo supercluster, which we will explore in a later chapter. For now, our focus remains on galaxy groups and clusters as distinct entities, the fundamental building blocks of these even larger cosmic structures. Galaxy groups, like our local group, typically contain fewer than 50 significant galaxies within volumes spanning 5 to 10 million light-years. They represent the most common galactic assemblages in the universe, comprising about half of all observed galaxies. Within these groups, gravitational interactions frequently occur, with smaller galaxies orbiting larger ones, and occasional mergers, resulting in the formation of ever larger galactic systems. Moving up in scale, we encounter galaxy clusters, substantially larger and more massive than groups. The nearest major cluster to Earth, the Virgo cluster, lies approximately 54 million light-years away in the constellation Virgo. This enormous collection contains more than 1,500 galaxies within a volume approximately 10 million light-years in diameter. Unlike the local group, which is dominated by spiral galaxies, the Virgo cluster features massive elliptical galaxies at its core, including Messier 87, one of the largest galaxies in our cosmic neighborhood. The Virgo cluster's total mass exceeds 1 quadrillion solar masses, roughly 100 times greater than our local group. Most of this mass exists as hot, diffuse gas, filling the space between galaxies, and as dark matter surrounding the entire cluster. The visible galaxies themselves constitute less than 1% of the cluster's total mass, yet they trace the underlying distribution of this invisible matter. At the heart of the Virgo cluster, several enormous elliptical galaxies dominate. These galaxies, including Messier 87, 84, and Messier 60, have grown to their current sizes by consuming smaller galaxies over billions of years. Surrounding this central region, thousands of smaller galaxies orbit, many showing signs of distortion from gravitational interactions. The entire cluster rotates slowly, completing one revolution over timescales of billions of years. The space between galaxies in the Virgo cluster contains hot, diffuse gas reaching temperatures of tens of millions of degrees. This intergalactic medium emits X-rays detectable by space-based observatories and contains nearly 10 times more ordinary matter than the cluster's galaxies themselves. Heavy elements within this gas, including oxygen, iron, and silicon, indicate that it originated partly from material ejected from galaxies through supernovae and galactic winds. Moving to even more massive examples, the Coma cluster, located about 320 million light-years from Earth, in the constellation Coma Berenices, contains more than 1,000 galaxies concentrated in a volume similar to the Virgo cluster. More compact than Virgo, the Coma cluster's galaxies pack more densely, creating an environment where galactic interactions occur more frequently. At the cluster's center, two supergiant elliptical galaxies, NGC 4889 and NGC 4874, each containing trillions of stars, dominate the landscape. The Fornax cluster, approximately 65 million light-years from Earth, offers another interesting example. Smaller than either Virgo or Coma, with about 60 large galaxies and several hundred dwarf galaxies, the Fornax cluster demonstrates a different stage of cluster evolution. Its central galaxy, NGC 1399, has grown to enormous proportions by consuming smaller neighbors, a process astronomers call galactic cannibalism. This process appears more advanced in Fornax than in larger clusters, suggesting that smaller clusters may evolve more rapidly. Perhaps the most impressive galaxy cluster within the reach of current telescopes is the Perseus cluster, located about 240 million light-years from Earth. This enormous collection contains thousands of galaxies, with a total mass of approximately 1,000 trillion solar masses. At its center lies NGC 1275, a supergiant elliptical galaxy spanning nearly 2 million light-years, more than 20 times wider than our Milky Way. Galaxy clusters reveal their presence in several ways beyond the visible light of their constituent galaxies. The hot intergalactic gas filling these clusters emits X-rays, allowing specially equipped telescopes to map their extent and structure. Additionally, galaxy clusters act as gravitational lenses, bending light from more distant objects as it passes through the cluster's gravitational field. This lensing effect provides astronomers with a method to measure the cluster's total mass, including its invisible dark matter component. The dynamics within galaxy clusters create fascinating environments quite different from the relatively serene conditions in isolated galaxies. Within clusters, galaxies move at speeds exceeding 1,000 kilometers per second relative to one another. These high-speed encounters can strip gas from galaxies, a process called ram pressure stripping, effectively halting new star formation. This explains why cluster environments typically contain higher proportions of elliptical and lenticular galaxies, which lack the gas reserves necessary for creating new stars. Another process, known as galaxy harassment, occurs when repeated high-speed encounters gradually distort a galaxy's structure. Spiral galaxies entering clusters may lose their delicate spiral patterns through these interactions, transforming into lenticular or elliptical shapes over billions of years. The most extreme interactions result in galaxy mergers, where two galaxies combine to form a single, larger system. Evidence of such mergers appears frequently in cluster environments, with many galaxies displaying disturbed shapes, tidal tails, or unusual star-forming regions. The formation and evolution of galaxy clusters reveals much about the universe's overall development. Clusters begin as slight overdensities in the distribution of matter shortly after the Big Bang. Over billions of years, gravity enhances these overdensities, drawing in additional material from surrounding regions. The largest clusters today occupy regions that were marginally denser than average in the early universe, demonstrating how small initial differences amplify over cosmic time. Galaxy clusters continue to grow through several mechanisms. Individual galaxies or small groups fall inward from the surrounding environment, following trajectories determined by the cluster's gravitational field. Occasionally, entire clusters collide and merge, creating even larger structures. The Bullet Cluster, located approximately 3.7 billion light-years from Earth, provides a spectacular example of such a collision in progress, with two massive clusters passing through each other at speeds exceeding 4,000 kilometers per second. These cluster collisions represent the most energetic events known in the universe since the Big Bang itself. When clusters collide, the galaxies within them typically pass by one another without direct impacts, due to the vast distances separating individual galaxies. However, the diffuse gas filling the space between galaxies does collide, heating to temperatures exceeding 100 million degrees and emitting intense X radiation. These collisions provide astronomers with natural experiments revealing the behavior of dark matter, which passes through the collision zone without interacting directly with either ordinary matter or itself. The largest known galaxy cluster, El Gordo, Spanish for the Fat One, lies approximately 7 billion light-years from Earth. This enormous structure, formerly known as ACT 0102-4915, contains hundreds of galaxies and a mass equivalent to several quadrillion suns. Its discovery at such a great distance challenges current understanding of how quickly such massive structures could form in the early universe. Recently formed galaxy clusters often display irregular shapes and substructures, indicating their ongoing assembly from smaller units. More mature clusters typically exhibit more regular, spherical distributions, suggesting that they have had sufficient time to settle into stable configurations. The Coma cluster, with its remarkably symmetrical appearance, represents one of the most evolved clusters in our cosmic neighborhood. The space between galaxy clusters contains diffuse filaments of gas and dark matter, forming bridges that connect neighboring clusters. These filaments, difficult to observe directly, reveal themselves through subtle effects on background radiation and the distribution of foreground galaxies. They represent the transition regions between the high-density environments within clusters and the relatively empty voids that separate them. Galaxy clusters serve several important functions in the cosmic ecosystem. They act as gravitational anchors, their enormous masses influencing the motion of matter across billions of light-years. They serve as natural laboratories for studying extreme physics, their hot intergalactic gases, and intense gravitational fields, creating conditions impossible to replicate on Earth. And they function as cosmic time capsules, their properties reflecting the conditions present when they first began to form, billions of years in the past. The organization of clusters themselves reveals patterns at even larger scales. Galaxy clusters tend to align along filaments, forming chains that can span hundreds of millions of light-years. The Perseus-Pisces supercluster, which we will explore in more detail in a later chapter, represents one such chain containing dozens of galaxy clusters, arranged in a filamentary structure over 500 million light-years long. In regions where multiple filaments intersect, particularly massive clusters often form. The Shapley supercluster, located approximately 700 million light-years from Earth, occupies such a nexus, containing dozens of rich galaxy clusters within a volume spanning 150 million light-years. Such regions represent the largest concentrations of mass in the observable universe, excluding structures so large that they cannot be considered gravitationally bound entities. When we observe galaxy clusters across different cosmic epochs, we witness their evolution over billions of years. Distant clusters, whose light began its journey to Earth when the universe was much younger, typically appear smaller, more irregular, and more actively star-forming than nearby examples. This evolutionary progression mirrors that seen in individual galaxies, suggesting common developmental patterns operating across multiple scales. The most distant clusters currently known exist as they appeared when the universe was less than 3 billion years old, less than a quarter of its current age. These early clusters contain fewer and smaller galaxies than their modern counterparts, with higher proportions of irregular and spiral types. Over the intervening billions of years, these clusters have likely grown substantially through accretion and mergers, potentially evolving into structures resembling the massive clusters we observe in our cosmic neighborhood. What determines the upper size limit for galaxy clusters? Several factors come into play. As the universe expands, it becomes increasingly difficult for gravity to gather material from ever more distant regions, limiting cluster growth. Additionally, the universe's accelerating expansion, attributed to dark energy, actively works against the gravitational assembly of matter on the largest scales. Finally, the finite age of the universe means that light, and therefore information, has traveled only a limited distance since the Big Bang, creating a natural horizon beyond which causal connections cannot yet exist. Despite these limitations, the universe has had nearly 14 billion years to assemble these massive structures. In regions where the initial distribution of matter was particularly dense, gravity has drawn together enormous quantities of material, creating the spectacular clusters we observe today. The most extreme examples, like El Gordo and the Bullet Cluster, push against the theoretical limits of how large such structures could become within the age of our universe. As we prepare to leave the realm of galaxy clusters behind, it's worth reflecting on the progression of scale in our journey. We began with human dimensions, measuring objects in meters. We expanded to planetary scales, with objects spanning thousands to hundreds of thousands of kilometers. We explored stellar scales, with objects measuring millions to billions of kilometers across. Star clusters introduced us to structures spanning tens to hundreds of light years. Galaxies expanded our view to structures spanning tens of thousands to millions of light years. Now, with galaxy clusters, we've entered a domain where objects span tens of millions of light years, distances so vast that light itself requires tens of millions of years to cross them. Yet even galaxy clusters, these enormous cosmic metropolises housing thousands of galaxies, represent merely the building blocks of the next level in our cosmic hierarchy. When we step back far enough to observe not just individual clusters but their arrangement across billions of light years, we discover the largest coherent structures known to exist, the cosmic web, with its vast filaments, nodes, and voids spanning significant fractions of the observable universe. Galaxies dance together in clusters, pulled by gravity across invisible threads. These threads, when viewed at sufficient scale, reveal themselves as the filaments of the cosmic web, the subject of our next exploration. To continue our journey of scale, we must expand our vision once more to encompass these vast, interconnected structures that define the largest patterns in our universe. Even in chaos, there is order, a delicate architecture spanning billions of light years. As we expand our view to ever larger scales, individual galaxy clusters begin to lose their distinctiveness. Like stepping back from a pointillist painting, where individual dots blend into a coherent image, our cosmic perspective reveals patterns that transcend the clusters themselves. We discover that galaxy clusters are not randomly distributed throughout space. Instead, they arrange themselves along vast filaments, surrounding immense voids, creating a structure that astronomers call the cosmic web. This web represents the largest coherent structure in the observable universe, a vast network of interconnected filaments spanning billions of light years. To comprehend this structure, imagine a three-dimensional spider web expanded to cosmic proportions, with galaxy clusters occupying the nodes where filaments intersect. Between these filaments stretch vast cosmic voids, regions of relative emptiness spanning hundreds of millions of light years. The first hints of this web-like structure emerged in the 1980s, when astronomers conducted the first systematic surveys of galaxy positions across large volumes of space. The Harvard-Smithsonian Center for Astrophysics survey, completed in 1985, mapped over 1,000 galaxies across a thin slice of the observable universe. The resulting map revealed something unexpected: galaxies clustered along distinct filaments surrounding conspicuous voids. Rather than distributing uniformly or randomly through space, galaxies appeared to trace the outlines of enormous bubbles. Subsequent surveys expanded this view dramatically. The 2-degree Field Galaxy Redshift Survey, completed in 2002, mapped the positions of over 200,000 galaxies. The Sloan Digital Sky Survey, an ongoing project begun in 2000, has mapped the positions of more than 3 million galaxies across roughly 40% of the sky. These surveys confirmed and elaborated upon the earlier findings, revealing the cosmic web in unprecedented detail. The filaments comprising this web typically span distances of 100 to 300 million light-years in length, with widths of approximately 6 to 10 million light-years. They consist primarily of dark matter, with galaxies tracing their contours like lights, decorating the branches of a Christmas tree. These galaxies make up less than 1% of the filament's total mass, the vast majority existing as invisible dark matter detectable only through its gravitational effects. Where multiple filaments intersect, massive galaxy clusters form. These nodes of the cosmic web contain the highest concentrations of both visible and dark matter, creating the deepest gravitational wells in the universe. Surrounding these nodes, slightly less dense regions contain smaller galaxy groups and individual galaxies arranged along the connecting filaments. Between the filaments lie cosmic voids, enormous regions of relative emptiness spanning 100 to 400 million light-years across. These voids contain far fewer galaxies than average, with the largest voids appearing almost entirely empty to current observational techniques. The Boötes void, one of the largest known, spans approximately 330 million light-years in diameter and contains remarkably few galaxies, despite its enormous volume. The contrast between the densest regions of the cosmic web and these voids is striking. The centers of massive galaxy clusters contain matter densities thousands of times greater than the cosmic average. The voids, conversely, contain less than 1/10 the average density. This stark difference creates a highly textured universe, with matter concentrated along distinctive patterns rather than distributed uniformly throughout space. This web-like structure was not always present. In the early universe, matter distributed much more evenly, with only slight variations in density from one region to another. These initial variations, imprinted during the first fraction of a second after the Big Bang, provided the seeds from which the cosmic web would eventually grow. Over billions of years, gravity amplified these initial variations. Slightly denser regions attracted additional matter from their surroundings, becoming progressively denser. Slightly less dense regions surrendered their matter to neighboring overdensities, becoming progressively emptier. This process, operating across cosmic time, transformed the nearly uniform early universe into the highly structured cosmic web we observe today. Computer simulations allow astronomers to reconstruct this evolution in remarkable detail. Starting with the slight density variations measured in the cosmic microwave background radiation, the afterglow of the Big Bang itself, these simulations apply the known laws of physics to track how matter would move and cluster over billions of years. The resulting virtual universes display striking similarities to the actual cosmic web observed by galaxy surveys, confirming our understanding of how these enormous structures formed. The cosmic web influences the evolution of the galaxies within it in numerous ways. Galaxies residing in filaments experience different environments than those in voids or cluster nodes. Filament galaxies have access to a steady supply of gas flowing along the filament, potentially fueling extended star formation. They also experience more frequent interactions with neighboring galaxies than would occur in less dense environments. Galaxies falling into cluster nodes along filaments often experience dramatic transformations. As they encounter the hot diffused gas pervading the cluster, their own gas reserves can be stripped away, halting star formation. This process, combined with more frequent galaxy interactions, helps explain why cluster environments contain higher proportions of elliptical and lenticular galaxies. While spiral galaxies predominate in less dense regions, the largest voids contain their own distinctive galaxy populations. Void galaxies tend to be smaller, bluer, and more actively star-forming than average. They also display lower metallicity, meaning they contain smaller proportions of elements heavier than hydrogen and helium. These characteristics suggest that void galaxies evolved with minimal external influence, in stark contrast to the heavily interactive environments found in filaments and clusters. The cosmic web provides a framework for understanding gas flows throughout the universe. Computer simulations indicate that vast amounts of hydrogen gas, much of it undetectable by current instruments, flows along filaments toward cluster nodes. This gas, heated by gravitational compression and shocks as it falls inward, eventually reaches temperatures of millions to tens of millions of degrees, becoming visible in X-ray observations of galaxy clusters. The scale of the cosmic web strains our capacity for visualization. The largest filaments span more than 1 billion light-years, distances so vast that light itself, traveling at 300,000 kilometers per second, requires more than 1 billion years to traverse them. The largest voids encompass volumes that could contain tens of thousands of galaxies like our Milky Way. The entire structure extends across the observable universe, spanning approximately 93 billion light-years in diameter. This enormous scale raises profound questions about the nature of the universe beyond our observable horizon. Does the cosmic web continue indefinitely? Do its characteristics change at even larger scales? Current observations suggest that the web becomes increasingly uniform when viewed at scales larger than about 300 million light-years, with the distribution of galaxies appearing more homogeneous at truly vast distances. This homogeneity aligns with the cosmological principle, the idea that the universe looks roughly the same from any vantage point when observed at sufficiently large scales. The topology of the cosmic web reveals much about the universe's underlying physics. The specific patterns we observe, with their characteristic filaments, nodes, and voids, align remarkably well with models incorporating dark matter and dark energy. Models lacking these components fail to reproduce the observed web-like structure, providing indirect evidence for the existence of these mysterious cosmic components. Dark matter, which interacts only through gravity and not through electromagnetic forces, plays a crucial role in shaping the cosmic web. Its gravitational influence began clustering matter long before ordinary atoms could form stable structures. By the time stars and galaxies began to form, dark matter had already established the scaffolding of the cosmic web, guiding the distribution of visible matter along its predetermined framework. Dark energy, which drives the accelerating expansion of the universe, influences the web's evolution on the largest scales. As the universe expands at an ever-increasing rate, the growth of the largest structures slows and eventually halts. Filaments stop attracting additional material from their surroundings, and voids expand more rapidly than they empty. This process effectively freezes the cosmic web's largest features, preserving them as fossils of an earlier era when gravity dominated over the effects of dark energy. The cosmic web bears striking resemblances to other networks found in nature, despite the vast differences in scale. Its filamentary structure echoes patterns seen in neural networks, mycelial fungi, river systems, and even the large-scale structure of the human body's circulatory system. This similarity may reflect fundamental properties of how networks form under various constraints, a subject of ongoing research in fields ranging from cosmology to neuroscience. The analogy to neural networks proves particularly apt. Just as neurons in the brain connect through an intricate network of axons and dendrites, galaxies connect through the filaments of the cosmic web. Information flows through neural networks via electrochemical signals. In the cosmic web, matter flows along filaments under the influence of gravity. Both networks evolved from initially simpler states to their current complex configurations through processes of self-organization. The human brain contains approximately 86 billion neurons. The observable universe contains a similar number of galaxies, each containing billions of stars. This comparison invites contemplation of the universe as a kind of organism or information processing system. While purely metaphorical, Such analogies help us conceptualize structures too vast for direct human experience. They remind us that patterns of organization emerge at all scales, from the microscopic to the truly cosmic. The identification and mapping of specific features in the cosmic web presents significant observational challenges. Unlike galaxy clusters, which appear as distinct concentrations of visible objects, the filaments and voids of the cosmic web consist primarily of diffuse material spread across enormous volumes. Detecting these features requires innovative techniques and the combination of data from multiple observational methods. One effective approach involves mapping the positions of millions of galaxies in three-dimensional space, using their redshifts to determine distances from Earth. When these positions are plotted, the resulting distribution reveals the underlying cosmic web, with galaxies tracing its filaments and avoiding its voids. This method provides the most direct visualization of the web's structure, but requires extensive observational resources to map sufficient numbers of galaxies across large volumes of space. Another approach utilizes gravitational lensing, the bending of light by mass concentrations. As light from distant galaxies passes through the cosmic web, it experiences subtle distortions from the gravity of intervening matter. By analyzing the patterns of these distortions across large areas of the sky, astronomers can map the distribution of both visible and dark matter, revealing the full extent of the cosmic web beyond what galaxies alone would indicate. A third method involves observing the faint emission or absorption of light by diffuse gas within the cosmic web. The vast majority of ordinary matter in the universe exists not in stars or galaxies, but in the form of diffuse hydrogen and helium gas, permeating intergalactic space. This gas, heated to temperatures between 10,000 and 10 million degrees Celsius, can absorb or emit light at specific wavelengths, creating signatures detectable by sensitive instruments. Combining these and other techniques, astronomers have identified numerous specific structures within the cosmic web. The Sloan Great Wall, discovered in 2005, stretches more than 1.3 billion light-years across, making it one of the largest known structures in the universe. This wall, actually a complex of several connected filaments, contains numerous galaxy clusters arranged in a gently curving pattern visible in three-dimensional galaxy maps. The Hercules Corona Borealis Great Wall, identified in 2013, may extend even further, spanning up to 10 billion light-years. This enormous structure, detected primarily through the distribution of gamma-ray bursts, remains somewhat controversial, as its true extent and coherence are difficult to confirm with current observational techniques. The Boötes void, mentioned earlier, represents one of the most dramatic examples of cosmic emptiness. Discovered in 1981, this enormous void contains just 60 known galaxies within a spherical volume that could hold about 10,000 galaxies if filled at average cosmic density. Other notable voids include the local void adjacent to our local group of galaxies and the giant void in the constellation Eridanus spanning approximately 1 billion light-years. The distribution of these structures across the observable universe reveals interesting patterns at the very largest scales. Voids tend to arrange themselves in a foam-like configuration, reminiscent of soap bubbles in 3 dimensions. Filaments trace the boundaries where these bubbles meet, with galaxy clusters forming at the vertices where multiple bubbles intersect. This pattern, predicted by theoretical models of structure formation, emerges naturally from the interaction between gravity and cosmic expansion acting on initial density fluctuations. The cosmic web structure encodes information about conditions in the early universe, preserving a record of processes that occurred billions of years ago. The specific patterns we observe reflect both the nature of the initial density fluctuations imprinted during cosmic inflation, a period of accelerated expansion in the first fraction of a second after the Big Bang, and the subsequent interaction between ordinary matter, dark matter, and radiation as the universe expanded and cooled. Aspects of the cosmic web also provide tests of fundamental physics. The specific distribution of filament lengths and void sizes depends on properties of dark matter, including how fast these particles moved in the early universe and whether they interact with each other through forces beyond gravity. By comparing the observed web to simulations incorporating different dark matter properties, astronomers can constrain the nature of this mysterious component that makes up approximately 85% of the universe's matter. Similar tests apply to dark energy, the even more mysterious component driving the universe's accelerated expansion. The growth rate of cosmic structures depends sensitively on how dark energy has evolved over cosmic history. By measuring this growth rate at different epochs, astronomers can distinguish between competing models of dark energy, including Einstein's cosmological constant, and more exotic alternatives in which dark energy changes over time. Beyond its scientific significance, the cosmic web holds philosophical implications. Its vast scale and intricate structure remind us that organization emerges at all levels in the universe, from subatomic particles to superclusters of galaxies. What appears as chaos at one scale may reveal remarkable order when viewed from a different perspective. The universe, despite its enormous size and complexity, follows understandable patterns governed by relatively simple physical principles. The web's structure also illustrates the creative potential of gravity working over cosmic time. From the nearly uniform conditions following the Big Bang, gravity sculpted the intricate cosmic tapestry we observe today, with its rich hierarchy of structures from individual stars to the vast filaments spanning billions of light years. This process, operating without direction or intent, nevertheless produced a universe of remarkable beauty and complexity. As we prepare to leave the realm of the cosmic web behind and explore even larger structures, it's worth reflecting on our journey thus far. We began with human dimensions, measuring objects in meters. We expanded to planetary scales, with objects spanning thousands to hundreds of thousands of kilometers. We explored stellar scales, with objects measuring millions to billions of kilometers across. Star clusters introduced us to structures spanning tens to hundreds of light years. Galaxies expanded our view to structures spanning tens of thousands to millions of light years. Galaxy clusters broadened our perspective to structures spanning tens of millions of light years. Now, with the cosmic web, we've entered a domain where structures span hundreds of millions to billions of light years. Distances so vast that light itself, traveling since the early epochs of cosmic history, has only recently crossed them. Yet even the cosmic web, this vast network spanning the observable universe, reveals patterns at still larger scales. The filaments of the web do not distribute randomly, but instead form vast complexes, regions where multiple filaments concentrate to create the largest bound structures known to exist, superclusters of galaxies. To continue our journey of scale, we must expand our vision once more, to encompass these enormous galactic continents that represent the upper limit of gravitationally bound cosmic structures. Even in chaos, there is order, a delicate architecture spanning billions of light years. And within this architecture, certain regions stand out, concentrations so vast that they challenge our understanding of how quickly cosmic structures can form. These superclusters, the subject of our next exploration, represent the culmination of structure formation in our universe, the largest coherent objects in the cosmic landscape. These regions span the visible cosmos, and yet there are structures even larger. As we continue our journey through cosmic structures of increasing scale, we arrive at superclusters, the largest gravitationally bound systems in the universe. These enormous assemblages gather multiple galaxy clusters and groups into vast complexes spanning hundreds of millions of light years. Superclusters represent the culmination of hierarchical structure, formation, the final tier in the gravitational assembly of matter before reaching scales where the universe's expansion overcomes gravity's attractive force. Our own cosmic neighborhood belongs to such a structure, a region astronomers long identified as the Virgo supercluster. This collection spans approximately 110 million light-years and contains the Virgo cluster at its heart, along with our local group and approximately 100 other galaxy groups and clusters. Together, these groups contain over 30,000 galaxies, ranging from enormous ellipticals with trillions of stars to diminutive dwarfs with just a few million. Recent studies have revealed that the Virgo supercluster itself forms just one lobe of an even larger structure, the Laniakea supercluster, a name derived from Hawaiian words meaning immense heaven, identified in 2014 through detailed mapping of galaxy motions. Laniakea spans approximately 520 million light-years and contains approximately 100,000 galaxies with a combined mass of approximately 100 quadrillion solar masses. To visualize Laniakea's structure, imagine a vast, somewhat flattened complex with multiple lobes extending outward in different directions. The Virgo supercluster forms one of these lobes. Others include the Hydra Centaurus supercluster, the Pavo Indus supercluster, and the Southern supercluster. At the heart of Laniakea lies the Great Attractor, a gravitational anomaly toward which thousands of galaxies, including our Milky Way, flow at speeds of hundreds of kilometers per second relative to the cosmic expansion. This inward flow, detected through careful measurement of galaxy motions, defines Laniakea's boundaries. Within this vast volume, galaxies experience a net gravitational attraction toward the supercluster's central region. Beyond these boundaries, galaxies flow toward different gravitational centers, belonging to other superclusters in the cosmic web. The identification of Laniakea represents a significant shift in how astronomers define superclusters. Earlier definitions relied primarily on the apparent concentration of galaxies in three-dimensional space, identifying regions of higher than average galaxy density as potential superclusters. The newer approach incorporates velocity information, using galaxy motions to map the underlying gravitational landscape and identify coherent flows toward common attractors. This velocity-based approach better reflects the physical reality of these enormous structures. As the universe expands, structures larger than approximately 300 million light-years across begin to expand along with it. Their internal gravity, insufficient to overcome the cosmic expansion driven by dark energy. Laniakea and similar superclusters represent structures at this critical threshold, where gravity and expansion roughly balance. Within them, smaller structures like galaxy clusters remain tightly bound, while the supercluster, as a whole, expands more slowly than the surrounding universe. Moving beyond our local volume, we encounter numerous other supercluster complexes distributed throughout the observable universe. The Perseus-Pisces supercluster, located approximately 250 million light-years from Earth, spans over 300 million light-years in length, containing thousands of galaxies arranged in a distinctive filamentary structure. Unlike Laniakea, which displays a somewhat rounded overall shape, Perseus-Pisces extends in a remarkably straight line, forming one of the most prominent features in maps of our cosmic neighborhood. The Shapley supercluster, located approximately 700 million light-years from Earth, in the direction of the constellations Centaurus and Hydra, represents perhaps the most massive supercluster within 1 billion light-years of our position. This enormous complex contains at least 24 rich galaxy clusters, including some of the most massive known. The combined gravitational influence of Shapley's mass creates a measurable pull on all matter within hundreds of millions of light-years, including our local group and the entire Laniakea supercluster. The Hercules supercluster, located approximately 500 million light-years from Earth, demonstrates how superclusters connect to the larger cosmic web. This structure forms an elongated filament containing numerous galaxy clusters, including Abell 2151 and Abell 2199. The Hercules supercluster appears to connect with neighboring structures, including the Shapley supercluster, through tenuous filaments of galaxies and gas, illustrating how discrete superclusters form parts of continuous networks spanning billions of light-years. The Horologium Reticulum supercluster, located approximately 700 million light-years from Earth, spans approximately 550 million light-years and contains at least 30 major galaxy clusters. Its overall structure resembles a curved sheet or wall, with galaxy clusters concentrated along several parallel filaments. This sheet-like morphology reflects the typical geometry of the cosmic web at the largest scales, where matter arranges itself along two-dimensional surfaces surrounding three-dimensional voids. The Corona Borealis supercluster, located approximately 1 billion light-years from Earth, spans approximately 100 million light-years and contains 7 rich galaxy clusters, packed into a remarkably small volume. This dense concentration creates one of the strongest gravitational anomalies known in the universe, causing measurable distortions in the cosmic microwave background radiation through an effect called the Sunyaev-Zeldovich effect, where photons from the early universe gain energy when passing through the supercluster's hot gas. The Sloan Great Wall, discovered in 2005 through the Sloan Digital Sky Survey, represents the intersection of multiple supercluster regions. This enormous structure spans approximately 1.37 billion light-years, containing dozens of galaxy clusters arranged in a gently curving pattern. Rather than constituting a single bound structure, the Sloan Great Wall appears to be a chance alignment of several distinct superclusters, seen from our particular vantage point, illustrating the challenge of identifying discrete structures within the continuous cosmic web. The identification of such enormous structures raises interesting questions about the universe's overall homogeneity. According to the cosmological principle, a cornerstone of modern cosmology, the universe should appear roughly the same in all directions when viewed at sufficiently large scales, typically assumed to be around 300 million light-years. Structures larger than this scale should not show significant coherence or pattern. Yet surveys consistently reveal structures spanning billions of light-years, potentially challenging this fundamental assumption. The discovery of the Hercules Corona Borealis Great Wall, identified in 2013 through the distribution of gamma-ray bursts, pushed this tension to new extremes. This structure may span up to 10 billion light-years, approximately 1/9 the diameter of the observable universe. If confirmed as a genuine coherent structure, it would represent a significant challenge to current cosmological models, which struggle to explain how such enormous patterns could form within the universe's 13.8 billion year history. However, the interpretation of these largest structures remains controversial. What appears as a single coherent structure from our particular vantage point might represent the chance alignment of multiple independent structures along our line of sight. Additionally, the methods used to identify such distant, diffuse structures involve complex statistical analyses vulnerable to subtle biases and misinterpretations. Even setting aside these most extreme examples, well-confirmed superclusters like Laniakea and Shapley present fascinating laboratories for studying cosmology and structure formation. Their properties provide crucial tests for theories regarding the universe's composition and evolution. The specific size, shape, and mass distribution of superclusters depends sensitively on the properties of dark matter, dark energy, and the initial conditions following the Big Bang. Computer simulations of cosmic evolution have successfully reproduced supercluster-like structures using the standard Lambda-CDM cosmological model, which includes cold, dark matter, and a cosmological constant driving accelerated expansion. These simulations begin with the slight density variations measured in the cosmic microwave background radiation, then apply the known laws of physics to track how matter would move and cluster over billions of years under the influence of gravity and cosmic expansion. The resulting virtual universes display striking similarities to the actual superclusters observed in galaxy surveys. They reproduce not only the typical sizes and masses of these enormous structures, but also their filamentary and sheet-like morphologies, their hierarchical organization, from individual galaxies to enormous complexes, and their overall distribution throughout space. This agreement provides strong evidence that our current cosmological models capture the essential physics governing the universe's largest structures. The formation of superclusters occurs through a complex interplay between cosmic expansion and gravitational attraction. In the early universe, regions with slightly above average density expanded more slowly than their surroundings, gradually becoming denser relative to the cosmic average. Within these regions, subregions with even higher initial densities eventually collapsed to form galaxies and galaxy clusters. These clusters then drew together under their mutual gravitational attraction, forming the superclusters we observe today. This process continues in the present universe, but faces increasing opposition from dark energy, which accelerates the universe's expansion and progressively weakens gravity's influence over larger distances. Structures already bound together, like galaxies and galaxy clusters, will remain intact indefinitely. Larger structures like superclusters, however, find themselves caught in a cosmic tug-of-war between their internal gravity and the universe's accelerating expansion. Simulations suggest that most superclusters will never coalesce into single-bound objects. Instead, they will gradually disperse as cosmic expansion overcomes their gravity, with their constituent galaxy clusters growing ever more isolated from one another. Over the next several 100 billion years, even nearby galaxy clusters will recede beyond each other's visibility horizons, each becoming an island universe unto itself, cut off from the broader cosmic context that current astronomers can observe. This eventual fate highlights an interesting aspect of superclusters. They represent structures caught at a critical threshold in cosmic evolution. Smaller structures formed earlier and will remain permanently bound. Larger structures never fully formed at all, remaining statistical associations within the cosmic web rather than physically bound systems. Superclusters exist at the boundary between these regimes, partly bound by gravity yet vulnerable to cosmic expansion, making them unique laboratories for studying the interplay between these competing influences. The total mass contained within superclusters staggers comprehension. The Laniakea supercluster contains approximately 100 quadrillion solar masses, or about 10,000 times the mass of the Milky Way galaxy. The Shapley supercluster may contain several times this amount. These enormous masses generate substantial gravitational fields, influencing the motion of matter across hundreds of millions of light years. Most of this mass exists as dark matter, the mysterious substance detectable only through its gravitational effects. Visible galaxies constitute less than 1% of a typical supercluster's total mass. Another 10 to 15% exists as hot, diffuse gas filling the space between galaxies, primarily within the galaxy clusters that form the supercluster's nodes. The remaining 85% exists as dark matter, forming a vast scaffolding that shapes the distribution of ordinary matter. This scaffolding extends far beyond the visible boundaries of superclusters, forming enormous halos that may span twice the diameter indicated by the visible galaxies alone. These extended halos overlap and connect with those of neighboring superclusters, creating the continuous cosmic web that spans the entire observable universe. When mapped in terms of total mass rather than visible galaxies, the boundaries between discrete superclusters become less distinct, revealing their nature as density peaks within a continuous distribution rather than isolated objects. The visible components of superclusters reveal interesting patterns reflecting their formation, history, and internal dynamics. The distribution of galaxy types varies systematically with environment, with elliptical and lenticular galaxies concentrated in dense cluster cores, and spiral galaxies more prevalent in filaments and outer regions. This pattern reflects the influence of environment on galaxy evolution, with denser regions accelerating the transition from gas-rich spirals to gas-poor ellipticals through processes like ram pressure, stripping, and frequent galaxy interactions. The gas between galaxies, detectable through its X-ray emission and other signatures, also varies systematically throughout superclusters. In cluster cores, this gas reaches temperatures of tens to hundreds of millions of degrees, emitting strongly in X-rays and affecting the properties of galaxies moving through it. In filaments connecting clusters, the gas cools to temperatures of 1 to 10 million degrees, becoming difficult to detect directly, but potentially containing a significant fraction of the universe's ordinary matter in what astronomers call the warm, hot, intergalactic medium. The circulation of this gas throughout superclusters creates a kind of cosmic ecosystem, with elements heavier than hydrogen and helium, forged within stars and released through supernovae, gradually enriching the intergalactic medium. These elements, including oxygen, carbon, and iron, eventually incorporate into new generations of stars and planets, creating a cycle of matter processing that operates on supercluster scales over billions of years. The motion of galaxies within superclusters reveals complex patterns reflecting both the universe's overall expansion and the local gravitational landscape. Galaxies generally move toward density peaks, flowing along filaments toward cluster nodes in a pattern called gravitational infall. Simultaneously, the entire supercluster participates in the universe's expansion, with more distant regions receding faster from any given point, following the Hubble flow that characterizes cosmic expansion. These competing influences create distinctive velocity structures within superclusters. Near dense cluster cores, galaxy motions appear randomized by the strong gravitational field, with speeds of about 1,000 kilometers per second in random directions. In filaments, galaxies move more coherently, flowing toward the nearest cluster at speeds of several hundred kilometers per second relative to the Hubble flow. In the least dense regions, galaxies primarily follow the Hubble flow, their motion dominated by cosmic expansion rather than local gravitational effects. The measurement of these complex motions provides one of the most effective methods for mapping the total mass distribution within and around superclusters, including the invisible dark matter component. By comparing the observed velocities with predictions from various mass models, astronomers can reconstruct the three-dimensional gravitational landscape shaping galaxy movements, a technique called velocity flow mapping. This technique revealed the extent of the Laniakea supercluster, showing that our Milky Way, along with the entire local group and Virgo cluster, flows toward the Great Attractor region near Laniakea's center at approximately 600 kilometers per second relative to the cosmic expansion. Similar analyses revealed that Laniakea itself moves toward the even more massive Shapley supercluster at nearly 1,000 kilometers per second, illustrating how gravitational influences propagate across hundreds of millions of light years. When viewed at the largest scales, these flow patterns reveal a surprisingly simple structure. Galaxies generally move away from void centers and toward filaments, along filaments toward cluster nodes, and along connected clusters towards supercluster cores. This pattern, sometimes described as the cosmic symphony, represents the combined influence of the universe's initial conditions, its subsequent evolution under gravity, and the accelerating expansion driven by dark energy. The future evolution of superclusters reflects this ongoing tension between gravity and expansion. Currently, the flow of matter towards supercluster cores continues in most regions, with galaxies and galaxy groups falling into clusters, and clusters drawing closer to one another within superclusters. However, the accelerating cosmic expansion progressively weakens gravity's influence over larger distances, eventually halting and reversing these inflows beyond certain scales. Simulations suggest that within our Laniakea supercluster, the Virgo cluster will continue to attract nearby galaxy groups, potentially including our local group, over the next several billion years. However, more distant components of Laniakea will gradually drift apart, their mutual gravitational attraction insufficient to overcome the expanding space between them. Eventually, these distant regions will recede beyond each other's cosmic horizon, becoming forever unreachable and ultimately unobservable from our vantage point. This process, operating throughout the universe, will gradually simplify cosmic structure at the largest scales. The intricate cosmic web will slowly dissolve as expansion stretches its filaments beyond recognition. Individual galaxy clusters, the nodes of this web, will remain as isolated islands in an increasingly empty universe. Superclusters, existing at the boundary between bound structures and the expanding cosmos, will disintegrate, their components scattered by dark energy's relentless influence. Our current view of superclusters thus represents a unique moment in cosmic history, a time when gravity has had sufficient time to assemble these enormous structures, but dark energy has not yet completely dispersed them. Had we evolved billions of years earlier, superclusters would appear less distinct, still in the process of formation. Billions of years in the future, they will have largely dissolved, with only their densest regions remaining as isolated galaxy clusters. As we prepare to leave the realm of superclusters behind and explore even larger structures, it's worth reflecting on our journey thus far. We began with human dimensions, measuring objects in meters. We expanded to planetary scales, with objects spanning thousands to hundreds of thousands of kilometers. We explored stellar scales, with objects measuring millions to billions of kilometers across. Star clusters introduced us to structures spanning tens to hundreds of light years. Galaxies expanded our view to structures spanning tens of thousands to millions of light years. Galaxy clusters broadened our perspective to structures spanning tens of millions of light years. The cosmic web revealed patterns spanning hundreds of millions to billions of light years. Now, with superclusters, we've examined structures that represent the largest gravitationally influenced systems in the universe, spanning hundreds of millions of light years and containing quadrillions of solar masses. Yet even superclusters do not represent the largest patterns in the cosmic landscape. When we examine the distribution of matter at scales beyond those where gravity can create bound structures, we discover even more extensive arrangements, vast walls and filaments that span significant fractions of the observable universe. These structures, which include the Sloan Great Wall and the even more extensive Hercules Corona Borealis Great Wall, represent the ultimate level in the hierarchy of cosmic structure, patterns so large that they challenge our understanding of how quickly such enormous features could form in the universe's 13.8 billion year history. These regions span the visible cosmos, and yet, there are structures even larger, the final patterns we will explore in our journey through cosmic scale, objects stretching across billions of light years that represent not gravity's cumulative work, but the faint echoes of conditions present in the first moments after the Big Bang. We may have reached the edge, not of the universe, but of our comprehension. As our journey through cosmic scales approaches its furthest extent, we encounter structures so vast that they challenge not only our imagination, but our understanding of how the universe evolved. These enormous patterns, spanning billions of light-years across significant fractions of the observable universe, represent the largest coherent structures yet identified. They exist at scales where, according to standard cosmological models, no significant patterns should persist, stretching the principles upon which modern cosmology rests. The Sloan Great Wall, discovered in 2005 by astronomers analyzing data from the Sloan Digital Sky Survey, represents one of the most dramatic examples of these largest structures. This enormous complex of galaxies, galaxy clusters, and connecting filaments stretches approximately 1.37 billion light-years across the northern sky, appearing as a gently curving band when mapped in 3 dimensions. For scale, this single structure spans about 1/68th of the diameter of the observable universe, a fraction that seems small until one considers the absolutely enormous baseline. To comprehend this scale, consider that light, traveling at 300,000 kilometers per second, requires over 1.3 billion years to cross from one end of the Sloan Great Wall to the other. During the time this light completes its journey, entire galaxies form, evolve, and merge. On Earth, life evolves from simple single-celled organisms to complex multicellular forms. The entire history of human civilization represents less than 0.1% of this duration. The Sloan Great Wall consists of dozens of galaxy clusters and superclusters, arranged in a distinct filamentary pattern, with galaxies concentrated along curved sheets surrounding enormous voids. Unlike smaller structures like individual galaxy clusters or even superclusters, the Great Wall does not represent a gravitationally bound object. Different regions of the wall experience no significant mutual gravitational attraction, their enormous separation ensuring that cosmic expansion dominates over gravity at these scales. Instead, the Great Wall represents a fossil of conditions present in the very early universe, an echo of quantum fluctuations that occurred during cosmic inflation. The period of accelerated expansion, believed to have occurred during the first fraction of a second after the Big Bang. These initial fluctuations, microscopically small at their origin, expanded with the universe itself, eventually growing to encompass billions of light years while retaining their original pattern. When the Sloan Great Wall was discovered, it briefly held the title of the largest known structure in the universe. Its enormous extent raised questions about the cosmological principle, the assumption that the universe appears roughly homogeneous when viewed at sufficiently large scales. Structures larger than about 300 million light-years should, according to this principle, blend into a relatively uniform distribution without significant patterns or preferred directions. The Great Wall, spanning more than 4 times this homogeneity scale, seemed to challenge this fundamental assumption. However, careful analysis suggested that while unusually large, the structure remained within the bounds of what might occasionally occur in a universe governed by standard cosmological models. Statistically speaking, the Great Wall represented an unusual but not impossible feature, given the enormous volume of the observable universe and the random nature of the initial density fluctuations from which cosmic structures evolved. This interpretation changed dramatically with the discovery in 2013 of an even larger structure, the Hercules Corona Borealis Great Wall. Identified through the distribution of gamma-ray bursts, the most energetic explosions known in the universe, this enormous complex may span up to 10 billion light-years, nearly 1/10 the diameter of the observable universe itself. If confirmed as a genuine coherent structure, it would dwarf all previously identified cosmic patterns, including the already enormous Sloan Great Wall. Gamma-ray bursts occur when massive stars collapse or when neutron stars collide, releasing enormous energy in focused beams that can be detected across billions of light-years. Because these events occur in galaxies, their distribution traces the underlying distribution of matter throughout the universe. When astronomers mapped several years' worth of gamma-ray burst detections, they noticed an unusual concentration in the direction of the constellations Hercules and Corona Borealis, suggesting the presence of an enormous overdensity of galaxies at distances between 6 and 10 billion light-years from Earth. This potential structure, spanning approximately tens of billions of light-years in volume, challenges current understanding of how quickly cosmic structures can form and how large they can grow. The universe's age, approximately 13.8 billion years, places fundamental limits on the speed at which gravitational forces can assemble matter into coherent patterns. For a structure spanning 10 billion light-years to form through gravitational processes alone, information would need to travel faster than light across the structure, violating a fundamental principle of Einstein's theory of relativity. However, the Hercules Corona Borealis Great Wall, if indeed a real structure rather than a statistical fluke or observational artifact, would not have formed through gravitational processes operating after the Big Bang. Instead, like all structures at these enormous scales, it would represent the expanded imprint of quantum fluctuations present during cosmic inflation, stretched to cosmic proportions by the universe's expansion. The question becomes not whether there was sufficient time for gravity to assemble such an enormous structure, but whether the initial conditions of the universe could contain fluctuations large enough to produce patterns spanning such a significant fraction of the observable universe. Standard inflationary models predict that quantum fluctuations during cosmic inflation should produce density variations across a wide range of scales, following a specific statistical pattern called a nearly scale-invariant spectrum. This pattern allows for larger fluctuations at larger scales, but with progressively decreasing amplitude. The existence of structures as large as the potential Hercules Corona Borealis Great Wall would require fluctuations at the extreme end of this spectrum, testing the limits of what these models can accommodate. Alternatively, the apparent structure might represent a statistical fluke in the distribution of observed gamma-ray bursts, a possibility that astronomers cannot yet definitively rule out, given the relatively small number of such bursts detected to date. Distinguishing between a genuine cosmic structure and a chance alignment requires additional observations and more sophisticated statistical analyses, efforts that continue as astronomers gather more data on these most distant and energetic events. The potential existence of these enormous structures raises profound questions about the fundamental nature of our universe. The cosmological principle, the assumption that the universe appears roughly the same in all directions when viewed at sufficiently large scales, forms a cornerstone of modern cosmological models. If structures spanning significant fractions of the observable universe actually exist, this principle may require modification or reinterpretation. One possibility involves a concept called cosmic variance. In a universe born from quantum fluctuations, the specific pattern of structures we observe from our particular vantage point represents just one realization of a random process. Other observers in distant regions of the universe would see different patterns with structures of various sizes and arrangements. What appears to us as an unusually large structure might represent a rare but not impossible statistical outcome, analogous to occasionally tossing 10 heads in a row when flipping a fair coin many times. Another possibility suggests that our observable universe itself might constitute just a small portion of a much larger, perhaps infinite cosmos. In such a scenario, what we perceive as extremely large structures might represent relatively small features within this larger context. This interpretation aligns with certain inflationary models that predict the existence of a multiverse, where our observable universe represents just one bubble within a vastly larger and older structure. A third possibility involves modifying our understanding of cosmic inflation itself. Alternative inflationary models can produce different spectra of initial density fluctuations, potentially allowing for larger variations at the largest scales than standard models predict. These models remain consistent with most cosmological observations, while accommodating the existence of structures spanning billions of light-years. Regardless of the interpretation, the search for and study of these largest cosmic structures pushes observational astronomy to its limits. Mapping patterns spanning billions of light-years requires surveying enormous volumes of space with sufficient detail to identify subtle variations in the distribution of galaxies or other traces of underlying matter. This effort involves multiple observational techniques, from traditional optical galaxy surveys to studies of the cosmic microwave background radiation, gravitational lensing effects, and the distribution of gamma-ray bursts and other distant objects. Beyond their theoretical importance, these enormous structures present a stunning visual perspective when mapped in 3 dimensions. The Sloan Great Wall appears as a gently curving band of enhanced galaxy density, weaving through space like an enormous cosmic snake. Individual galaxies within this structure, each containing billions of stars, appear as mere points, too numerous to discern individually. Galaxy clusters, themselves enormous by human standards, form just local concentrations along this vast filament, like cities along a cosmic highway. The specific shape of the Sloan Great Wall reflects its origin in the early universe. Rather than forming a simple straight line, it curves gently through space, potentially representing a small segment of an even larger structure that extends beyond the survey volume. This curvature, combined with variations in density along the wall's length, preserves information about the specific pattern of quantum fluctuations present during cosmic inflation, providing a fossil record of conditions present in the first fraction of a second after the Big Bang. The internal structure of these enormous walls and filaments reveals fascinating patterns reflecting their formation history. Like the cosmic web at smaller scales, these largest structures consist of interconnected filaments, sheets, and nodes, with galaxies and galaxy clusters concentrated along filaments and at their intersections. Enormous voids, regions nearly devoid of galaxies, separate these filaments, creating a foam-like pattern extending across billions of light-years. This arrangement maximizes the distance between overdense and underdense regions while minimizing the surface area separating them, an optimal configuration that emerges naturally from the interplay between gravity and cosmic expansion acting on initial density variations. The specific pattern reflects the composition of the early universe, particularly the relative abundances of ordinary matter, dark matter, and radiation during the universe's first several 100,000 years. The largest structures also provide natural laboratories for studying the universe's overall expansion history. Light from galaxies within these structures began its journey to Earth billions of years ago, when the universe was much younger and expanding at a different rate than today. By measuring the exact distances to thousands of galaxies distributed throughout these enormous volumes, astronomers can reconstruct how cosmic expansion has changed over time, providing crucial tests of theories regarding dark energy, the mysterious component driving accelerated expansion. The potential Hercules Corona Borealis Great Wall presents particular significance in this regard, as it spans distances corresponding to times when the universe was just 3 to 5 billion years old, less than half its current age. Measurements across such an enormous structure could reveal how dark energy's influence has evolved over cosmic history, distinguishing between competing models that make different predictions about the universe's past and future development. The discovery of these largest structures has involved remarkable technological and methodological innovations. The Sloan Digital Sky Survey, which revealed the Sloan Great Wall, represents one of astronomy's most ambitious observational projects, systematically mapping millions of galaxies across a quarter of the entire sky. This effort involved constructing a dedicated telescope equipped with specialized instruments capable of measuring the distances to hundreds of galaxies simultaneously, then processing the resulting data with sophisticated algorithms to identify patterns spanning billions of light-years. The identification of the potential Hercules Corona Borealis Great Wall relied on even more exotic observations, detecting brief flashes of gamma rays from some of the most energetic events in the universe. These gamma-ray bursts, lasting typically from milliseconds to minutes, required specialized space-based detectors designed to capture these fleeting signals from across the cosmos. Determining the distances to these bursts involved rapidly notifying ground-based telescopes to observe the fading afterglows before they disappeared, a process requiring international coordination and rapid response protocols. These technological achievements highlight how our understanding of the universe's largest structures depends on our ability to detect the faintest signals from the most distant objects. Each advance in observational capability reveals previously undetected patterns, potentially including structures even larger than those currently known. Future projects, including the Vera Rubin Observatory and the Euclid and Nancy Grace Roman Space Telescopes, will map cosmic structures with unprecedented detail and depth, potentially revealing whether the Hercules Corona Borealis Great Wall represents the largest structure in the observable universe, or merely the largest yet detected. The study of these largest structures also connects to research on the cosmic microwave background radiation, the oldest light in the universe, released approximately 380,000 years after the Big Bang, when the universe first became transparent to radiation. This ancient light, now cooled to just 2.7 Kelvin above absolute zero, preserves a snapshot of conditions in the early universe, including the seeds of all future cosmic structures. Detailed maps of this radiation, produced by satellites like NASA's Wilkinson Microwave Anisotropy Probe and the European Space Agency's Planck mission, reveal subtle temperature variations, reflecting density differences in the early universe. These variations, typically just 1 part in 100,000, represent the embryonic forms of structures that would eventually evolve into galaxies, galaxy clusters, and the enormous walls and filaments we observe today. Comparing the patterns observed in the cosmic microwave background with the distribution of galaxies billions of years later provides a crucial test of cosmic evolution models. The specific statistical properties of these patterns, including their size, distribution, and spatial arrangement, should evolve in predictable ways under the influence of gravity and cosmic expansion. Any significant discrepancies between predictions and observations could indicate problems with current cosmological models or the need for new physics to explain the universe's largest structures. Some anomalies have indeed emerged from these comparisons. The cosmic microwave background contains several unexpected features, including an unusual alignment of temperature patterns across the largest scales, sometimes called the axis of evil, and a large cold spot spanning approximately 1.8 billion light-years that may indicate the presence of an enormous void or more exotic phenomenon. These features, while not definitively connected to structures like the Sloan Great Wall or the potential Hercules Corona Borealis Great Wall, suggest that the universe at its largest scales may contain surprises not fully explained by current theories. The possible existence of structures approaching or exceeding the scale of the observable universe raises profound questions about the limits of scientific knowledge. The observable universe itself spans approximately 93 billion light-years in diameter, a finite volume determined by the distance light could have traveled since the Big Bang, accounting for cosmic expansion. Any structures larger than this scale would extend beyond our potential observation, regardless of technological advances, their full extent forever hidden beyond our cosmic horizon. This horizon represents not merely a practical limitation but a fundamental epistemic boundary. We cannot observe, even in principle, anything beyond this distance, as insufficient time has elapsed since the universe's birth for light or any other signal to reach us from greater distances. While we can develop theoretical models describing what might exist beyond this horizon, these models remain intrinsically unverifiable through direct observation. The largest known structures, spanning significant fractions of this observable volume, thus approach the fundamental limits of empirical science. They exist at scales where traditional notions of causality and structure formation break down, where the universe's finite age and the light speed limit constrain our ability to fully comprehend their nature and origin. In this sense, they represent not merely the largest things in the universe, but the boundary of what we can meaningfully study and understand. This boundary creates interesting philosophical implications for how we define biggest in a cosmic context. Structures like the Sloan Great Wall and the potential Hercules Corona Borealis Great Wall span billions of light-years, enormous distances by any standard. Yet they represent collections of galaxies and galaxy clusters, not single coherent objects. Their identity as distinct things depends on how we define boundaries and coherence at these largest scales, where gravity produces limited binding effects and cosmic expansion progressively dominates. Moreover, their status as the biggest structures depends on the specific criteria used for measurement. By spatial extent, these enormous walls and filaments certainly qualify for consideration. But alternative metrics might yield different candidates. By mass, the largest individual galaxy clusters contain more concentrated matter than equivalent volumes of these walls. By gravitational influence, superclusters create stronger local effects than the more diffuse larger structures. By binding energy, individual galaxies represent more coherent systems than any larger structure. This ambiguity in defining biggest reminds us that scale involves not merely quantitative measurement, but qualitative assessment of what constitutes a meaningful structure at different cosmic levels. As we approach the limits of observable scale, these distinctions become increasingly important, reflecting the transition from gravitationally bound systems to statistical patterns spanning significant fractions of the observable universe. Perhaps most profoundly, these larger structures remind us of the limitations inherent in human comprehension. Our brains evolved to understand our immediate environment, objects and distances relevant to our survival. We can intellectually grasp the concepts of billions of light years and structures spanning significant fractions of the observable universe, but we cannot intuitively comprehend such scales. They exceed not merely our physical experience, but our capacity for genuine understanding. In this sense, we may have reached the edge, not of the universe, but of our comprehension. The largest cosmic structures exist at scales where our intuitions fail, where familiar concepts like distance, time, and causality operate differently than in our everyday experience. They challenge us to develop new frameworks for understanding, new ways of conceptualizing structure, and scale beyond human referenced measurements. As we prepare to leave behind these largest defined structures and consider the universe as a whole, it's worth reflecting on our journey thus far. We began with human dimensions, measuring objects in meters. We expanded to planetary scales, with objects spanning thousands to hundreds of thousands of kilometers. We explored stellar scales, with objects measuring millions to billions of kilometers across. Star clusters introduced us to structures spanning tens to hundreds of light years. Galaxies expanded our view to structures spanning tens of thousands to millions of light years. Galaxy clusters broadened our perspective to structures spanning tens of millions of light years. The cosmic web revealed patterns spanning hundreds of millions to billions of light years. Superclusters showed us the largest, gravitationally influenced systems spanning hundreds of millions of light years. Now, with structures like the Sloan Great Wall and the potential Hercules Corona Borealis Great Wall, we've examined patterns spanning billions of light years, approaching the limits of what our observable universe can contain. This progression represents not merely an increase in size, but an expansion of perspective, a journey from human-centered measurement to cosmic scale. At each level, new patterns emerge, new physical processes dominate, new insights develop about the universe's structure and evolution. The journey reveals a cosmos of remarkable complexity and order, with recognizable patterns repeating across vast differences in scale, from the arrangement of planets around stars to the distribution of galaxies along cosmic filaments. Yet, as we approach the largest scales, traditional notions of structure and coherence begin to dissolve. The universe transitions from a collection of distinct objects to a continuous web of matter and energy, with boundaries and identities becoming increasingly arbitrary designations, rather than physically meaningful distinctions. At the very largest scales, the cosmos approaches the homogeneous and isotropic ideal described by the cosmological principle. Though perhaps with larger fluctuations than initially expected, we may have reached the edge, not of the universe, but of our comprehension. And in this humbling recognition lies perhaps the most profound insight of our scale journey, that the cosmos exists independently of our ability to fully grasp it, extending beyond not just our physical reach, but our conceptual frameworks. The largest cosmic structures, spanning billions of light years, represent not just enormous collections of matter, but the boundary between what we can observe and what lies forever beyond our horizon, between what we can measure and what we can truly comprehend. Sometimes the answer depends on the question, and sometimes the question becomes the mystery. As our journey through cosmic scales approaches its conclusion, we must confront a deceptively simple question that has guided our exploration. What does it mean for something to be biggest in the universe? This question, which initially seemed straightforward, reveals surprising complexity when examined across the vast range of cosmic structures we've encountered. The definition of biggest depends critically on the specific criteria we choose to measure, each yielding different candidates for the title of largest cosmic entity. Size represents perhaps the most intuitive measure of biggest, referring to the physical extent or diameter of an object or structure. By this criterion, the largest known structures are the enormous walls and filaments we explored in the previous chapter, spanning billions of light years across significant fractions of the observable universe. The potential Hercules Corona Borealis Great Wall, if confirmed as a genuine coherent structure, would span approximately 10 billion light years, making it the largest known pattern in the cosmos by spatial extent. However, size alone provides an incomplete perspective on cosmic scale. Volume, the three-dimensional space occupied by an object or structure, offers a related but distinct measure. While enormous filaments like the Sloan Great Wall extend across billions of light years, they occupy relatively thin sheets or strands within this volume. By contrast, cosmic voids, the nearly empty regions between filaments, encompass much larger volumes, despite lacking obvious visible features. The Boötes void, spanning approximately 330 million light-years in diameter, contains a volume of approximately 19 quadrillion cubic light-years, largely devoid of galaxies or other significant structures. Mass provides yet another measure of biggest, focusing on the total amount of matter contained within an object or structure, rather than its spatial extent. By this criterion, superclusters represent the largest coherent structures, containing quadrillions of solar masses, within volumes spanning hundreds of millions of light-years. The Shapley supercluster, with an estimated mass of more than 10 to the 16th solar masses, contains more concentrated matter than longer, but less dense structures like the Sloan Great Wall. However, even superclusters contain only a small fraction of the universe's total mass. The cosmic web as a whole, including all galaxies, clusters, filaments, and voids within the observable universe, contains approximately 10 to the 23rd solar masses of ordinary matter and approximately 5 times this amount in dark matter. This entire mass, while enormous by human standards, represents just 4.9% of the observable universe's total energy content, with the remaining 95.1% existing as dark energy distributed uniformly throughout space. This observation leads to another potential definition of biggest energy content. By this measure, dark energy, the mysterious component driving the universe's accelerated expansion, represents the dominant contribution to the cosmos. Within the observable universe, dark energy contains approximately 5.4 times 10 to the 71st joules, dwarfing the energy contained in all forms of matter combined. Unlike matter, which clusters into distinct structures, dark energy appears to distribute uniformly throughout space, making the universe itself the only meaningful container for this dominant energy component. Gravitational influence offers yet another perspective on cosmic scale, measuring how strongly an object affects its surroundings through the force of gravity. Individual black holes, despite their relatively small physical size, generate gravitational fields of extraordinary intensity, warping space-time in their vicinity to create event horizons from which nothing, not even light, can escape. Supermassive black holes, residing at the centers of most large galaxies, can contain billions of solar masses, compressed into regions smaller than our solar system, creating gravitational influences that shape entire galactic cores. At larger scales, galaxy clusters represent the most gravitationally dominant structures, their combined mass creating deep gravitational wells that affect matter across tens of millions of light-years. The most massive known galaxy cluster, El Gordo, contains approximately 2 quadrillion solar masses, generating a gravitational field strong enough to measurably bend light from more distant galaxies, passing through its vicinity, creating spectacular examples of gravitational lensing. The concept of gravitational binding introduces another important distinction when considering cosmic scale. Gravitationally bound structures remain permanently connected by mutual gravitational attraction, maintaining their overall integrity despite the universe's expansion. Individual galaxies, galaxy groups, and galaxy clusters qualify as gravitationally bound structures. Superclusters exist at the boundary, with their densest regions bound, but their outer regions gradually separating due to cosmic expansion. Larger structures like the Sloan Great Wall lack gravitational binding entirely, their components receding from one another as space itself expands between them. This distinction creates an interesting perspective on what constitutes a meaningful thing at different cosmic scales. Gravitationally bound structures form distinct entities with relatively clear boundaries and long-term stability. Unbound structures represent statistical patterns in the distribution of matter, their identity more conceptual than physical, their boundaries somewhat arbitrary, and their long-term existence subject to erasure by cosmic expansion. From this perspective, galaxy clusters might qualify as the biggest things in the universe, while larger structures represent patterns rather than discrete objects. Density provides yet another criterion for evaluating cosmic scale, measuring the concentration of matter within a given volume rather than its total extent or mass. By this measure, the centers of neutron stars represent the densest known stable objects in the universe, packing approximately 2 solar masses of material into spheres just 20 kilometers in diameter. This creates densities approaching 1 billion tons per cubic centimeter, so extreme that atomic nuclei dissolve into a sea of neutrons and other exotic particles. Black holes represent the ultimate in density, with their mass concentrated at central singularities of effectively zero volume, creating infinite density at their cores according to current physical theories. However, black holes can be meaningfully measured only by their event horizons, the boundaries beyond which nothing can escape their gravitational pull. The largest known black hole, at the center of the galaxy, TON 6-1-8, has an event horizon spanning approximately 119 billion kilometers, larger than 20 times the orbit of Pluto around our Sun. Complexity offers a more qualitative measure of scale, focusing on the internal organization and information content of cosmic structures rather than their physical dimensions. By this criterion, galaxies represent remarkably complex systems containing hundreds of billions of stars, complex patterns of gas and dust, and intricate dynamics shaped by the interplay of gravity, radiation, magnetic fields, and other forces. The Milky Way alone contains approximately 1 septillion stars, planets, moons, asteroids, comets, and other discrete objects, each with its own unique characteristics and history. Yet even galaxies pale in complexity compared to certain structures they contain. A single planet, hosting complex life, such as Earth, contains more information and organizational complexity than entire galaxies of lifeless matter. Earth's biosphere, comprising all living organisms and their relationships with the environment, represents one of the most complex systems known, with millions of distinct species engaged in countless ecological relationships across diverse habitats. This observation suggests that, biggest in terms of complexity, may direct our attention not toward the largest structures but toward the richest in information and organization. Longevity provides another dimension for considering cosmic scale, measuring objects not by their spatial extent, but by their duration through time. Stars represent remarkably long-lived entities, with the smallest red dwarfs capable of stable hydrogen fusion for up to 10 trillion years, nearly 1,000 times the current age of the universe. By contrast, even the largest cosmic structures prove relatively ephemeral in the longest-term cosmic perspective. The accelerating expansion of the universe will eventually disperse all unbound structures, with even gravitationally bound systems like galaxy clusters ultimately dissolving as protons and other particles decay over timescales of perhaps 10 to the 40 years. The most stable known structures may be the supermassive black holes found at the centers of most large galaxies. According to current theories, these entities will persist for approximately 10 to the 100th years, gradually evaporating through Hawking radiation until they vanish in final bursts of energy. This timeline exceeds the current age of the universe by a factor of 10 to the 90th, making these black holes effectively eternal from any practical human perspective. This temporal dimension reminds us that cosmic scale encompasses not just space but time, with the universe's evolution continuously transforming the structures it contains. The biggest structures we observe today did not exist in the early universe and will eventually disappear in the far future as cosmic expansion accelerates and matter gradually decays. Scale thus varies not just across spatial dimensions but throughout cosmic history, with different structures dominating at different epochs. Consciousness introduces yet another dimension to consider, albeit one that ventures beyond purely physical measures into philosophical terrain. If consciousness, awareness, or subjective experience represents something fundamental, rather than merely emergent from physical processes, then entities containing consciousness might qualify for consideration when evaluating cosmic scale from certain philosophical perspectives. Earth, as the only planet definitely known to host conscious beings, would stand out in this context, despite its modest physical dimensions. This perspective shifts attention from external size to internal experience, from objective measurement to subjective awareness. While speculative, it reminds us that significance does not always correlate with physical scale. A single conscious entity might encompass more meaning, value, or significance than vast but insensate cosmic structures, depending on one's philosophical framework. Moving beyond specific criteria to more general considerations, we might ask whether focusing on discrete things makes sense at all when discussing the largest cosmic scales. The universe transitions from distinct objects at smaller scales to continuous distributions at larger ones, with boundaries becoming increasingly arbitrary and identification of discrete structures more an artifact of human categorization than physical reality. Perhaps the universe itself, as a totality encompassing all other structures, represents the only meaningful candidate for biggest thing at the largest scales. Yet even the universe proves challenging to define precisely in this context. Our observational access extends only to the observable universe, the region from which light has had sufficient time to reach Earth since the Big Bang, given the finite speed of light and the universe's finite age. This observable universe spans approximately 93 billion light-years in diameter due to cosmic expansion, containing approximately 2 trillion galaxies within this enormous volume. However, cosmological theories strongly suggest that the universe extends far beyond this observable region, potentially to infinity. Inflationary models, which align well with observational evidence, indicate that our observable universe represents just a minuscule fraction of a vastly larger, perhaps infinite cosmos. If correct, this perspective renders the question of biggest meaningless at the largest scales, as infinity admits no meaningful comparison of relative size. Multiverse theories introduce even greater complexity, suggesting that our universe might represent just one of many universes, perhaps with different physical constants, different dimensions, or different fundamental laws. These multiverses, if they exist, transcend not just spatial scale, but the very framework within which we typically understand physical existence. Their potential vastness defies not just measurement but comprehension, existing beyond the realm of empirical science and entering the domain of theoretical speculation. This progression from everyday human scales to multiverses spans approximately 63 orders of magnitude, from objects measured in meters to structures spanning quintillions of meters. Throughout this range, the meaning of biggest continuously evolves, with different criteria yielding different candidates at different scales. No single answer to the question, what is the biggest thing in the universe, suffices across this entire spectrum of cosmic scale. Perhaps the most meaningful approach involves recognizing this plurality of perspectives rather than seeking a single definitive answer. The universe presents not one scale but many, not one type of structure, but a rich hierarchy from subatomic particles to superclusters and beyond. Different measures of biggest highlight different aspects of this cosmic hierarchy, each providing insight into the various ways matter and energy organize across space and time. This multiplicity of perspectives reminds us that scale itself represents a human construct, a framework we impose upon reality to make sense of it. The universe exists independently of our measuring systems, our categorizations, our distinctions between things, and the relationships between them. Our understanding of scale, while based on empirical observation, nevertheless reflects human cognitive patterns and limitations rather than intrinsic features of cosmic reality. In this context, the question, what is the biggest thing in the universe, reveals more about our modes of understanding than about the universe itself. It reflects our tendency to categorize, to compare, to establish hierarchies of size and significance. It demonstrates our remarkable capacity to comprehend scales far beyond direct human experience through mathematics, technology, and abstract reasoning. And it highlights the limits of this comprehension when faced with the true vastness of cosmic scales. As we prepare to explore the observable universe as a whole in the next chapter, it's worth reflecting on this journey through cosmic scale. We began with human dimensions, progressively expanding our perspective through planets, stars, galaxies, and the largest known structures. At each level, we encountered not just larger versions of familiar objects, but qualitatively different types of organization, different physical processes, different relationships between components. This progression revealed a universe of remarkable diversity across scales, with patterns emerging, dissolving, and re-emerging in different forms as we zoomed outward. It demonstrated how scale influences not just size but nature, with gravity, electromagnetism, nuclear forces, and cosmic expansion dominating at different levels. And it highlighted the tension between human comprehension, evolved for navigating terrestrial environments, and cosmic reality, extending across billions of light years and billions of years. Sometimes the answer depends on the question, and sometimes the question becomes the mystery. The search for the biggest thing in the universe leads ultimately not to a single definitive answer, but to deeper questions about measurement, meaning, and the limits of human understanding. It reminds us that the cosmos exists not as a collection of distinct objects arranged by size, but as an interconnected whole that we perceive differently at different scales of observation. Perhaps this insight itself represents the most significant outcome of our scale journey, more meaningful than any specific answer to the original question. In seeking the biggest thing, we discover that the universe defies simple categorization, transcending our measuring systems and challenging our conceptual frameworks. The mystery lies not in identifying the largest structure, but in comprehending a cosmos where scale itself proves relative, contingent, and ultimately incomplete as a description of reality. We've reached the furthest edge of what light can show us, but is that all there is? As our journey through cosmic scales approaches its outermost boundary, we arrive at the observable universe itself, the totality of space and time, accessible to our observations. This vast domain, spanning approximately 93 billion light-years in diameter, represents not the entire universe, but the finite portion visible from our particular vantage point, limited by the fundamental constraints of light, speed, and cosmic age. Beyond this horizon lies space we cannot see, matter and energy, forever beyond our observational reach, regardless of technological advancement. To understand the observable universe, we must first clarify what observable means in this context. When astronomers use this term, they refer to regions from which light or other signals could have reached Earth since the Big Bang, given the finite speed of light and the finite age of the universe. This creates a spherical volume centered on Earth, with a radius determined by how far light could have traveled during the universe's 13.8 billion-year history. However, this radius does not equal 13.8 billion light-years, as one might initially expect. Due to cosmic expansion, the space through which light travels continuously stretches while the light journeys toward us. Light, arriving today from the most distant observable regions, began its journey just 380,000 years after the Big Bang, when the universe first became transparent to radiation. In the intervening 13.8 billion years, the space carrying this light has expanded dramatically, stretching the distance between the emission point and Earth to approximately 46.5 billion light-years. This creates an observable universe with a diameter of approximately 93 billion light-years, containing an estimated 2 trillion galaxies distributed throughout this enormous volume. If each of these galaxies contains an average of 100 billion stars, the observable universe houses approximately 2 times 10 to the 23rd stars, a number so vast it exceeds the count of grains of sand on all of Earth's beaches by a factor of approximately 10,000. The total mass of ordinary matter within the observable universe equals approximately 10 to the 23rd solar masses, equivalent to approximately 2 times 10 to the 53rd kilograms. This includes all stars, planets, interstellar gas, dust, and other forms of matter composed of standard atomic particles. However, ordinary matter constitutes just 4.9% of the observable universe's total energy content, with dark matter contributing 26.8% and dark energy the remaining 68.3%. When visualized in 3 dimensions, the observable universe forms a perfect sphere centered on Earth, leading to the superficial impression that we occupy a special position in the cosmos. However, this spherical symmetry represents merely a consequence of how observation works, rather than any cosmic privilege status. Every point in the universe has its own observable sphere with the same radius, each containing largely the same cosmic structures, viewed from different angles and perspectives. No location occupies a central position in the universe as a whole, consistent with the cosmological principle that the universe lacks any preferred location or direction when viewed at the largest scales. This principle, a cornerstone of modern cosmology, states that the universe appears roughly homogeneous and isotropic when observed at sufficiently large scales, typically above a few 100 million light-years. Homogeneity means that matter distributes approximately uniformly throughout space, with no region containing significantly more galaxies than any other region of equal volume. Isotropy means that the universe looks approximately the same in all directions, with no preferred axis or orientation. Observational evidence strongly supports this principle, though with some intriguing exceptions. Galaxy surveys reveal that when averaged over volumes spanning hundreds of millions of light-years, galaxy distribution approaches uniformity, with approximately the same number of galaxies per unit volume in all regions. The cosmic microwave background radiation, the afterglow of the Big Bang itself, displays remarkable isotropy, with temperature variations of just 1 part in 100,000 across the entire sky. However, structures like the Sloan Great Wall and the potential Hercules Corona Borealis Great Wall, spanning billions of light years, suggest larger inhomogeneities than expected under the strictest interpretation of the cosmological principle. These enormous patterns represent statistical fluctuations in the distribution of matter, potentially stretching the boundaries of what current cosmological models can comfortably accommodate within standard frameworks. The observable universe contains an estimated 10 to the 80th atoms, a number so large it defies intuitive comprehension. To put this figure in perspective, there are more atoms in the observable universe than there are grains of sand on all beaches on Earth, multiplied by the number of stars in the observable universe, multiplied by the number of neurons in a human brain. Each of these atoms most likely originated in the nuclear furnaces of long-vanished stars, forged through nuclear fusion from primordial hydrogen and helium, created in the first few minutes after the Big Bang. The current average density of ordinary matter in the observable universe equals approximately 5 hydrogen atoms per cubic meter, a vacuum far more perfect than anything achievable in terrestrial laboratories. This remarkably low density results from cosmic expansion, stretching the original matter of the universe across ever-increasing volumes throughout cosmic history. In the universe's earliest observable moments, matter existed at densities exceeding those found in atomic nuclei, with all the mass currently spread across billions of light-years compressed into a volume smaller than a subatomic particle. The observable universe contains not just matter and energy, but space-time itself, the four-dimensional fabric in which all cosmic events occur. According to Einstein's general theory of relativity, this space-time curves in response to mass and energy, creating what we experience as gravity. Massive objects like stars and planets create local curvatures in space-time, while the total mass-energy content of the observable universe determines its overall geometric properties. Current measurements indicate that the observable universe has remarkably flat geometry on the largest scales, with parallel lines remaining approximately parallel, even when extended across billions of light years. This flatness implies that the universe's total energy density almost exactly equals the critical value required for a flat geometry, a coincidence that inflationary models explain as the natural outcome of exponential expansion in the universe's earliest moments, which would have stretched any initial curvature to near-perfect flatness. The observable universe contains not just space but time, encompassing all events from the Big Bang to the present moment. This cosmic history divides into several distinct epochs, each characterized by different physical conditions and dominant processes. The earliest directly observable epoch, the recombination era, occurred approximately 380,000 years after the Big Bang, when the universe cooled sufficiently for electrons to combine with atomic nuclei, forming neutral atoms and allowing light to travel freely through space for the first time. This light, now cooled by cosmic expansion to just 2.7 Kelvin above absolute zero, forms the cosmic microwave background radiation observable throughout the universe. This ancient radiation provides our most distant direct observation, a kind of cosmic wall beyond which we cannot directly see using electromagnetic radiation. The universe existed before this moment, but remained opaque to light, preventing direct observation of earlier epochs through conventional telescopes. After recombination, the universe entered the cosmic dark ages, a period lasting several hundred million years, when no stars or galaxies yet existed to illuminate the expanding cosmos. During this era, slight overdensities in the distribution of matter gradually grew under the influence of gravity, eventually reaching sufficient density to trigger the formation of the first stars and galaxies. This cosmic dawn, occurring approximately 100 million to 1 billion years after the Big Bang, ended the Dark Ages and began the process of reionization, when radiation from the first luminous objects stripped electrons from neutral hydrogen throughout intergalactic space. The following billions of years saw the progressive assembly of cosmic structure, with galaxies forming, merging, and evolving into the patterns we observe today. The peak of star formation occurred approximately 10 billion years ago, when the universe generated new stars at rates about 10 times higher than the current epoch. Since then, cosmic star formation has steadily declined as gas supplies deplete and the accelerating expansion makes it increasingly difficult for gravity to assemble new stars. and galaxies. Approximately 5 billion years ago, when the universe had reached about half its current age, cosmic expansion began to accelerate under the influence of dark energy. This acceleration, confirmed by observations of distant supernovae in the late 1990s, represented a profound shift in cosmic evolution, transitioning from a gravity-dominated era of structure formation to an expansion-dominated era characterized by the progressive isolation of gravitationally bound systems from one another. This cosmic history remains imprinted in the observable universe's current structure, with different distances corresponding to different periods in cosmic evolution. When we observe galaxies billions of light years away, we see them not as they exist now, but as they appeared billions of years ago, when the light now reaching Earth first departed. This creates a unique observational situation where looking outward in space simultaneously means looking backward in time, with the most distant observable regions showing the universe in its infancy. This relationship between distance and time creates a cosmic timescale corresponding to different observational horizons within the observable universe. Galaxies 1 billion light-years away appear as they existed 1 billion years ago. The most distant observable galaxies, more than 13 billion light-years away, appear as they existed less than 1 billion years after the Big Bang. The cosmic microwave background radiation reveals the universe as it appeared just 380,000 years after its birth. Each distance represents a different epoch in cosmic history, all simultaneously visible from our current vantage point. The observable universe thus functions as both a spatial and temporal totality, containing not just everything we can potentially see, but everything we can potentially know through direct observation. This finite sphere represents the fundamental limits of empirical astronomy, the boundary beyond which we must rely on theoretical extrapolation rather than observational evidence. While we can develop models describing what might exist beyond this horizon, these models remain intrinsically unverifiable through direct observation. Within this observable sphere, astronomers have identified structures spanning an enormous range of scales, from planets just thousands of kilometers in diameter to the enormous walls and filaments stretching billions of light-years across significant fractions of the observable volume. These structures form a distinct hierarchy, with smaller components assembling into progressively larger systems under the influence of gravity, creating the complex cosmic web we observe today. At the largest scales, this web displays a foam-like structure, with galaxy clusters and superclusters arranged along filaments surrounding vast voids, largely devoid of visible matter. This pattern emerges naturally from the interplay between the universe's initial conditions, the attractive force of gravity, and the repulsive effect of dark energy driving accelerated expansion. Computer simulations applying the known laws of physics to model cosmic evolution reproduce this structure with remarkable fidelity, confirming our basic understanding of how the observable universe developed its current configuration. The total information content of the observable universe presents another fascinating perspective on its scale. Physicists estimate that the observable universe contains approximately 10 to the 120th bits of information, based on the maximum entropy possible within its volume. This figure far exceeds the information storage capacity of all human-created devices, all human brains combined, or even all the atoms in the Milky Way galaxy. The observable universe represents not just the largest physical system accessible to our observation, but the largest information repository, containing the accumulated result of 13.8 billion years of physical processes operating across billions of light-years. Despite its enormous scale, the observable universe represents just a finite sample of what likely exists beyond our cosmic horizon. Inflationary cosmological models, which align well with observational evidence, suggest that the universe extends far beyond the observable region, potentially to infinity. If correct, this perspective renders our observable universe, despite its vastness, as infinitesimal compared to the cosmos as a whole, similar to how a single grain of sand relates to all the beaches on Earth. This potential infinity raises profound questions about uniqueness and significance. If the universe extends infinitely, basic probability suggests that any configuration of matter possible under the laws of physics occurs not just once, but infinitely many times. This would imply the existence of infinitely many regions identical to our observable universe, containing the same galaxies, stars, planets, and even identical copies of Earth, and all its inhabitants, along with infinitely many regions with slight variations and completely different configurations. Such speculation remains unverifiable through direct observation, belonging more to metaphysics than empirical science. However, it highlights how our understanding of the observable universe connects to broader questions about the nature of reality, the limits of knowledge, and humanity's place within the cosmic context. The observable universe represents not just the largest thing we can see, but the boundary of what we can empirically know about the cosmos. The observable universe changes over time due to two competing factors. As the universe ages, light from increasingly distant regions has sufficient time to reach Earth, gradually expanding the observable horizon. Simultaneously, cosmic expansion accelerates under the influence of dark energy, causing distant regions to recede at ever-increasing speeds. Eventually, roughly 100 billion years from now, these recession velocities will exceed the speed of light for all galaxies beyond our local group, causing them to permanently disappear from view as no signal will ever be able to bridge the expanding space between them. In this far future scenario, observers would inhabit a radically different observable universe, containing just a few dozen galaxies, rather than the trillions visible today. All evidence of the broader cosmic web, the Big Bang, and the universe's evolution would fade from direct observability, replaced by apparently empty space in all directions beyond the local galactic neighborhood. Without currently available observations, scientists in this future era might struggle to discover the true nature and history of the cosmos, highlighting how our current era represents a uniquely privileged observational window in cosmic history. The age of the observable universe, 13.8 billion years, represents just a moment in its potential future timeline. If protons prove stable over sufficiently long timescales, the universe could remain observable for approximately 10 to the 40 years before matter itself decays into radiation. Over this unimaginably vast duration, the observable region would progressively empty as galaxies exhaust their gas supplies, stars burn out, and black holes slowly evaporate through Hawking radiation. The final observable universe would contain nothing but extremely diffuse radiation, approaching but never quite reaching a state of maximum entropy or heat death. This temporal perspective reminds us that the observable universe exists not as a static entity, but as an evolving system, continuously changing throughout cosmic history. What we observe today represents just a single frame in an ongoing cosmic process, with both a detailed past and a potentially infinite future stretching beyond our lifetime, our civilization, and perhaps even the existence of matter as we understand it. The boundary of the observable universe, often called the particle horizon, represents not a physical edge, but an observational limit. The universe likely continues beyond this horizon, essentially identically to the regions within it, following the same physical laws and displaying similar large-scale patterns. No wall or edge marks this boundary, which exists purely as a consequence of light's finite speed and the universe's finite age. An observer located beyond our particle horizon would see a different observable universe centered on their location, just as valid and complete as our own. This multiplicity of potential observable universes, each centered on a different observational point, highlights the relative nature of cosmic horizons. The universe does not divide naturally into observable and unobservable regions. Instead, these categories depend entirely on the observer's specific location and time, with each point in space having its own unique observable sphere. What appears as a natural cosmic boundary from our perspective represents merely a contingent feature of our particular observational situation, rather than a fundamental physical structure. Despite this relativity of cosmic horizons, the observable universe represents a physically meaningful entity for any specific observer. The finite speed of light ensures that events beyond the particle horizon cannot causally influence the observer's present moment, creating a region of space-time fundamentally disconnected from current observations. This causal structure, sometimes called the light cone, divides the universe into regions that can potentially affect or be affected by the observer, and those forever outside causal contact due to the finite age of the universe and the limits imposed by light speed. The 93 billion light-year diameter commonly cited for the observable universe refers to the current proper distance to the particle horizon, measuring the stretched space between our position and the most distant regions we can potentially observe. However, when these most distant regions emitted the light now reaching us, they were much closer, separated by just approximately 42 million light-years, rather than 46.5 billion light-years. The vast difference between these figures results from cosmic expansion stretching space throughout the light's journey, increasing the current distance far beyond the original separation when the light began its voyage. This expansion continues to stretch the observable universe by approximately 7.2 kilometers per second per megaparsec of distance, a value known as the Hubble constant. At the edge of the observable universe, this expansion rate translates to recession velocities exceeding the speed of light, a possibility not forbidden by relativity because space itself expands rather than objects moving through space. This superluminal expansion ensures that some regions currently within our observable universe will eventually disappear from view, their light unable to overcome the ever-increasing stretching of intervening space. The total energy content of the observable universe includes not just the mass of ordinary matter and dark matter, but also the energy inherent in radiation, neutrinos, and the mysterious dark energy permeating all space. Current measurements indicate that this total energy equals approximately 1 × 10⁻70 joules, equivalent to the energy that would be released by converting approximately 1 × 10⁻53 kilograms of matter completely to energy, following Einstein's famous equation E = mc². This enormous energy, while vast by human standards, represents a remarkably small amount given the observable universe's volume. The energy density averages approximately 5 × 10⁻10 joules per cubic meter, a value so small that a cubic kilometer of seemingly empty space contains about the same energy as would be released by burning a single drop of gasoline. This tenuous energy distribution reflects the universe's enormous expansion from its initially compact state, spreading its original energy content across an ever-increasing volume throughout cosmic history. The average temperature of the observable universe equals approximately 2.7 Kelvin, just slightly above absolute zero. This temperature, measured precisely through observations of the cosmic microwave background radiation, represents the current value of what began as an extraordinarily hot initial state. In the universe's earliest observable moments, temperatures exceeded 1 trillion degrees, hot enough to prevent atoms or even atomic nuclei from forming. As the universe expanded, this initial thermal energy dispersed across increasing volumes, cooling progressively to its current frigid state. This cooling process has profound significance for the universe's structure and habitability. Only as the cosmos cooled below certain temperature thresholds could atoms form, stars ignite, and potentially habitable planets develop. The observable universe's current temperature exists in a Goldilocks zone of cosmic evolution, warm enough to sustain the nuclear reactions powering stars, yet cool enough to allow complex chemistry and potentially life. In the distant future, as the universe continues expanding and cooling, it will eventually become too cold to support conventional stars or life as we understand it, transitioning to an ever more diffuse and frigid state. The observable universe, then, represents not just the total accessible to our observations, but a specific moment in cosmic evolution when complexity reaches its potential zenith. Before this era, the universe remained too hot and dense for complex structures to form. After this era, spanning perhaps a few trillion years, the accelerating expansion and cooling will gradually simplify cosmic structure, eventually reducing the observable universe to an effectively empty void containing only diffuse radiation approaching absolute zero. This temporal perspective highlights how remarkable our current observational situation truly is. We exist during a cosmological moment when the observable universe displays maximum structural richness, with matter organized into atoms, stars, galaxies, and the intricate cosmic web. This complex configuration might represent a transient phenomenon in cosmic evolution, a brief window when the universe's expansion and cooling have proceeded sufficiently to allow complexity without yet dispersing it beyond recognition. The distribution of matter and energy throughout the observable universe reveals fascinating patterns reflecting its evolution. Ordinary matter, comprising stars, planets, gas, and dust, concentrates primarily along the filaments of the cosmic web, with the highest densities found in galaxy clusters at the intersection of multiple filaments, Dark matter forms a more extensive distribution, creating halos surrounding galaxies and clusters, while also extending along filaments at lower densities. Dark energy, believed responsible for accelerating cosmic expansion, distributes uniformly throughout all space, its density remaining constant, despite the universe's ongoing expansion. This distribution creates a distinctly textured universe rather than a homogeneous one, with matter concentrated in complex patterns surrounded by relatively empty voids. However, when averaged over sufficiently large volumes, this texture approaches uniformity, consistent with the cosmological principles expectation of large-scale homogeneity. This balance between local structure and global uniformity represents one of the observable universe's most distinctive features, reflecting both the amplification of initial density variations through gravitational processes and the limits imposed on this amplification by cosmic expansion. We've reached the furthest edge of what light can show us, but is that all there is? As we prepare to explore potential structures beyond the observable universe in our next chapter, we confront the fundamental limits of empirical knowledge. The observable universe, spanning 93 billion light-years in diameter and containing 2 trillion galaxies distributed throughout this enormous volume, represents the largest entity directly accessible to our observations. Yet theoretical models strongly suggest that this vast domain represents just a tiny fraction of a much larger, perhaps infinite cosmos extending far beyond our observational horizon. This tension between the finite observable and the potentially infinite unobservable raises profound questions about the nature of knowledge, the limits of science, and humanity's place within the cosmic context. The observable universe represents not just the largest thing we can see, but the boundary of what we can empirically know about the cosmos, the division between observation and speculation, between science and metaphysics. Beyond this boundary lie regions forever beyond our direct observation, accessible only through theoretical extrapolation and philosophical reflection. The universe may only be one note in a much larger symphony. As our journey through cosmic scales approaches its speculative frontier, we move beyond the observable universe to consider what might exist beyond our visual horizon. What structures, patterns, or phenomena might populate regions of space and time forever invisible to our telescopes? While such questions inevitably venture into theoretical terrain, they remain grounded in principles of physics and cosmology rather than mere fantasy. By extending our best physical models and following their logical implications, we can explore possibilities that, while unobservable, remain scientifically plausible. The most immediate extension beyond our observable universe involves simply more of what we already see, regions filled with additional galaxies, clusters, filaments, and voids following the same basic physical laws and displaying similar large-scale patterns. Standard cosmological models suggest that the universe extends far beyond our observable horizon, potentially to infinity, with matter and energy distributed according to the same statistical principles visible within our cosmic neighborhood. This extended cosmos, sometimes called the global universe, would contain countless additional observable regions centered on different vantage points, each encompassing a unique but statistically similar sample of the universe's overall structure. An observer located 1 trillion light-years from Earth would see an entirely different set of galaxies and large-scale structures, yet the overall patterns, distribution, and evolution would follow the same principles visible from our location. If the universe extends sufficiently far, basic probability suggests that any particular configuration of matter possible under the laws of physics must repeat infinitely many times. This would imply the existence of regions identical to our observable universe down to the smallest detail, including identical copies of the Milky Way, Earth, and even individual people. Between these identical regions would exist countless variations, regions differing by just one atom's position, by the outcome of a single quantum event, or by larger-scale differences in cosmic structure. This concept, sometimes called the Level I multiverse in physicist Max Tegmark's classification system, represents the most conservative extension beyond our observable horizon, requiring only that space extends sufficiently far while following the same physical laws we observe locally. While forever beyond direct confirmation, this scenario follows logically from infinite space, combined with the finite number of possible particle configurations within any bounded region. Moving to more speculative territory, inflationary cosmological models suggest the possibility of regions with fundamentally different physical properties than those observed within our horizon. According to these models, the universe underwent a period of exponential expansion during its first fraction of a second, stretching quantum fluctuations into the seeds of cosmic structure we observe today. This inflationary process, theoretical physicists suggest, might have ended at different times in different regions, creating distinct bubble universes with potentially different physical constants, dimensions, or even fundamental laws. These bubble universes, collectively forming what cosmologists call the inflationary multiverse or level 2 multiverse, would exist beyond our observable horizon. Separated by regions of space still undergoing inflation, the boundaries between these bubbles would expand faster than light, ensuring that different bubbles could never communicate or interact. Each bubble would effectively function as an independent universe with its own unique properties, potentially supporting radically different types of structure than those familiar from our cosmic neighborhood. The physical constants that determine our universe's structure, including the strength of gravity, the mass of elementary particles, and the strength of the electromagnetic force, might vary between these bubble universes. Some bubbles might have stronger gravity, creating universes where stars burn faster and galaxies form more quickly. Others might have different ratios between fundamental forces, potentially preventing atoms from forming or creating exotic alternative chemistries. Still, others might have additional spatial dimensions beyond the three we experience, allowing for structural possibilities inconceivable within our familiar geometrical framework. The vast majority of these bubble universes would likely prove inhospitable to life as we understand it, lacking the delicate balance of physical constants that allows for stable atoms, long-lived stars, and the complex chemistry underlying biological systems. A universe with slightly stronger gravity might collapse before stars could form, while one with weaker electromagnetic forces might prevent atoms from binding into molecules. This observation has led some theorists to propose the anthropic principle, suggesting that we inevitably observe a universe compatible with our existence because we could not exist to make observations in the vast majority of possible universes. Even more speculative are theories suggesting fundamentally different mathematical structures underlying reality in different regions beyond our cosmic horizon. String theory, a leading candidate for reconciling quantum mechanics with general relativity, suggests the possible existence of a landscape containing perhaps 10 to the 500th distinct vacuum states, each corresponding to a universe with different fundamental properties. This landscape, sometimes called the level 3 multiverse, would contain regions operating according to different low-energy approximations of the same underlying mathematical framework, potentially yielding dramatically different manifestations of physical reality. The most extreme extension, sometimes called the level 4 multiverse, proposes that all mathematically consistent structures exist as physical realities, independent of any specific physical laws or initial conditions. According to this perspective, advanced by Tegmark and others, physical reality itself represents nothing more or less than mathematical structure, with our observable universe corresponding to just one particular mathematical system among infinitely many possibilities. Other mathematical systems would manifest as entirely different types of universes, with properties potentially beyond our ability to conceptualize within our familiar physical framework. Between these speculative possibilities and the more conservative extensions of known physics lies a vast territory of potential structures, some perhaps accessible to indirect detection through their subtle effects on our observable region. Certain anomalies in the cosmic microwave background radiation, including the so-called cold spot, spanning approximately 1.8 billion light-years, might potentially indicate interactions with adjacent regions beyond our horizon, though conventional explanations within standard cosmological models remain more probable. Dark energy, the mysterious force driving the universe's accelerated expansion, might connect to structures beyond our observable horizon. Some theories suggest dark energy represents a form of vacuum energy associated with the intrinsic properties of space itself, potentially linking to the broader string theory landscape or other multiverse scenarios. If confirmed, such connections would suggest that the accelerating expansion currently observed within our horizon relates to larger structures and processes spanning regions forever beyond direct observation. Dark matter, which interacts with ordinary matter primarily through gravity, might form larger structures beyond our observational capabilities. Current observations reveal dark matter halos surrounding galaxies and extending along the filaments of the cosmic web, but the full extent of dark matter distribution remains unknown. Potentially, vast dark matter structures might span regions larger than the observable universe, detectable only through their subtle gravitational effects on the largest observable scales. Cosmic inflation itself, the hypothesized period of exponential expansion in the universe's first fraction of a second, connects to potential structures beyond our horizon. The mechanism driving inflation, typically modeled as a scalar field called the inflaton, might create diverse patterns and structures across regions vastly larger than our observable universe. The specific pattern of density fluctuations observed in our cosmic microwave background might represent just one statistical realization of a process operating across scales currently beyond our observational reach. The dimensionality of space represents another frontier where larger structures might exist beyond detection. String theory suggests the possible existence of additional spatial dimensions beyond the three we directly experience, compactified or curled up at scales too small for direct observation. Some theories propose that these extra dimensions might extend into larger structures beyond our observable horizon, creating geometric complexities inconceivable within our familiar three-dimensional framework. Topological features of spacetime might also create structures larger than the observable universe, just as a two-dimensional being living on the surface of a torus, donut shape, would experience locally flat geometry while inhabiting a globally curved space. Our three-dimensional observable universe might represent a local portion of a more complex topological structure. These global features, potentially including handles, bridges, or complex connectedness patterns, would extend beyond our observational horizon, while subtly influencing the largest observable scales. Even time itself might participate in larger structures beyond our detection capabilities. Some theoretical models suggest the possible existence of multiple time dimensions or complex temporal topologies, creating chronological structures far more intricate than the simple linear progression experienced within our observable universe. While such possibilities remain highly speculative, they highlight how our familiar conceptual frameworks might prove inadequate for describing the full extent of cosmic structure. The concept of information presents another perspective on potential larger structures. Theoretical physics increasingly recognizes information as a fundamental physical quantity rather than merely an abstract concept. The total information content of the observable universe, estimated at approximately 10 to the 120th bits, might represent just a small subset of a much larger informational structure spanning regions beyond our horizon. This perspective reframes cosmic structure in terms of information processing rather than merely matter and energy distribution. Quantum mechanics introduces additional possibilities for structures beyond conventional detection. According to some interpretations, particularly the many-worlds interpretation proposed by Hugh Everett III, quantum events generate branching realities, creating an ever-expanding tree of parallel universes representing all possible outcomes of quantum processes. While these branches exist within a larger mathematical structure called Hilbert space rather than conventional spacetime, they represent another form of cosmic structure, potentially far larger than our observable universe. The most radical extensions involve concepts partially or wholly beyond current scientific frameworks. Some theoretical approaches to quantum gravity suggest the possibility of baby universes, new cosmic regions, nucleating from our own through quantum processes, analogous to bubble formation in boiling water. These baby universes would expand into their own spacetime, potentially developing structures entirely separate from yet causally connected to our observable region through their origin point. Mathematician Roger Penrose has proposed a model called conformal cyclic cosmology, suggesting that our universe represents just one aeon in an infinite sequence, with each aeon's remote future connecting to the next aeon's Big Bang through a conformal transformation that matches the infinitely expanded state of one universe with the infinitely compressed state of the next. This model, if correct, would imply structures spanning not just beyond our spatial horizon, but beyond our temporal limits as well. Other theories suggest the possibility of structures existing within what we consider empty space, occupying dimensions or manifestations currently beyond our detection capabilities. The vacuum itself, far from representing true nothingness, contains quantum fluctuations, virtual particle pairs, and potentially more exotic phenomena that might connect to larger structures beyond conventional observation. Some speculative theories propose that what we perceive as empty space might represent a complex medium with internal structure far richer than currently recognized. The nature of consciousness introduces yet another dimension to these considerations. Some philosophers and scientists have proposed panpsychism, the view that consciousness or proto-conscious properties exist throughout the physical world as fundamental features of reality. If such views have merit, the universe might contain experiential structures vastly larger than any material formations, potentially spanning regions beyond our observable horizon. While such possibilities venture beyond conventional scientific frameworks, they highlight the potential limitations of purely materialist perspectives on cosmic structure. Between these speculative possibilities and the more conservative extensions of known physics lies a fundamental epistemic boundary. Structures truly beyond our observable horizon remain intrinsically unverifiable through direct observation, regardless of technological advancement. No telescope, regardless of its sophistication, can detect light that has not had sufficient time to reach us since the Big Bang. No experiment, regardless of its sensitivity, can directly measure phenomena causally disconnected from our local region of space-time. This limitation transforms questions about such structures from empirical investigations into different types of inquiry, combining mathematical consistency, theoretical elegance, explanatory power, and philosophical coherence. While we cannot observe a multiverse directly, we can evaluate whether multiverse theories provide more comprehensive explanations for observable phenomena, demonstrate greater mathematical consistency, or resolve theoretical puzzles more effectively than single universe models. The potential existence of structures larger than the observable universe highlights the distinction between physical reality and human knowledge. The universe exists independently of our ability to observe or comprehend it, potentially containing regions, dimensions, and phenomena forever beyond our epistemic reach. This perspective invites humility regarding cosmic understanding, acknowledging that our best theories and observations might reveal just a tiny fraction of a vastly larger and more complex reality. This epistemic boundary creates an interesting parallel with the historical progression of astronomical knowledge. Throughout human history, our understanding of cosmic scale has continuously expanded, from Earth-centered models encompassing just the visible planets to modern cosmology spanning billions of light years. Each expansion revealed previously unimagined structures, while demonstrating the limitations of earlier perspectives. The current boundary at our observable horizon might similarly represent just one stage in an ongoing expansion of understanding, with future theoretical developments revealing new dimensions of cosmic structure beyond current conceptualization. The universe may only be one note in a much larger symphony. As our journey through cosmic scales approaches its speculative frontier, we confront not just the limits of observation, but the boundaries of knowledge itself. The observable universe, spanning 93 billion light-years in diameter and containing trillions of galaxies, represents merely the visible portion of what might be an infinitely larger and more complex reality. What appears as the ultimate cosmic horizon from our current perspective might eventually be recognized as just one level in an endless hierarchy of structure extending far beyond our current conceptual frameworks. This perspective invites both intellectual humility and wonder. Humility in recognizing the inevitable limitations of human knowledge when confronting potentially infinite cosmic complexity. Wonder in contemplating the vast territories of reality potentially lying beyond our observational horizon, containing structures, patterns, and phenomena perhaps forever beyond direct detection, yet hinted at through theoretical implications and mathematical consistency. As we prepare to consider the universe as a whole in our next chapter, this speculative frontier reminds us that cosmic scale transcends not just human experience, but potentially human comprehension. The largest structures in the universe might extend far beyond what we can observe, measure, or even conceptualize within our familiar frameworks. In seeking the biggest thing, we discover not a definitive answer, but an endless horizon of possibility, stretching beyond the boundaries of knowledge itself. The question dissolves, because the universe is not just big, it may be without limit. As our journey through cosmic scales reaches its ultimate frontier, we confront the universe as a complete entity, the totality encompassing all space, time, matter, and energy. This concept represents the logical conclusion of our scale progression, the final and most comprehensive structure containing all others we have explored. Yet in approaching this ultimate level, we encounter profound questions about the nature of totality itself. Is the universe finite or infinite? Does it have a boundary or edge? What shape does it possess? And how can we meaningfully discuss the size of something that might transcend spatial limitation entirely? These questions transform our exploration from purely observational astronomy to the intersection of cosmology, mathematics, and philosophy. While our telescopes can probe only the observable universe, spanning 93 billion light-years in diameter, theoretical models and mathematical principles allow us to consider the potential nature of the cosmos as a whole, including regions forever beyond direct observation. Modern cosmological models, based on Einstein's general theory of relativity, combined with observational evidence from the cosmic microwave background and large-scale structure surveys, suggest three possibilities for the universe's overall geometry: flat, positively curved, closed, or negatively curved, open. These geometries correspond to specific relationships between the universe's actual density and a theoretical value called the critical density, which determines whether cosmic expansion will eventually halt and reverse, closed, continue at an ever-decreasing rate, flat, or expand eternally at a significant rate, open. Current measurements indicate that the universe's actual density matches the critical density almost exactly, suggesting flat geometry to within the limits of observational precision. In a flat universe, parallel lines remain parallel forever, and the familiar rules of Euclidean geometry apply even across cosmic distances. This flatness implies that if the universe is finite, it must have a non-trivial topology, similar to how a flat sheet of paper can form a finite surface when folded into a torus, donut shape, while maintaining locally flat geometry at every point. The question of whether the universe is finite or infinite cannot be answered definitively through current observations. A finite universe, even one vastly larger than our observable region, would contain a finite amount of matter organized into a finite number of galaxies, stars, and other structures. An infinite universe would extend endlessly in all directions, containing infinite matter organized into infinite structures following similar patterns to those observed within our cosmic horizon. Mathematical considerations suggest interesting implications for both possibilities. A finite universe, regardless of its exact size, would constitute just one possible configuration among countless alternatives, raising questions about its initial conditions and whether other universes might exist with different properties. An infinite universe would contain regions identical to our observable volume, repeated endlessly across cosmic distances, a consequence of the finite number of possible particle configurations within bounded regions combined with infinite spatial extent. The concept of infinity introduces profound conceptual challenges when applied to physical reality. A truly infinite universe would contain not just an arbitrarily large number of galaxies, but literally endless galaxies, not just vast distances, but literally boundless space. Such infinity transcends not just human experience, but potentially human comprehension, as our cognitive frameworks evolved to handle finite quantities relevant to survival rather than actual infinities. Some cosmologists question whether physical infinity makes theoretical sense, suggesting that while mathematics can handle infinite quantities coherently, physical reality might prove intrinsically finite, even if immeasurably vast. Others argue that infinite models provide the most elegant and consistent descriptions of cosmic geometry, avoiding the need for arbitrary boundaries or edges, while naturally explaining observed flatness through inflationary processes in the early universe. Inflationary cosmology, which proposes a period of exponential expansion during the universe's first fraction of a second, provides one framework for understanding the universe's potential vastness beyond our observable horizon. According to these models, our observable universe represents just a minuscule fraction of the post-inflationary cosmos, which might extend for at least 10 to the 26th times farther than our current observational limit. Some versions of inflation, called eternal inflation, suggest that the process continues indefinitely in some regions, creating an infinite and ever-expanding universe containing countless bubble universes with potentially different physical properties. The shape or topology of the universe represents another dimension of its overall structure. General relativity allows for various global geometries consistent with local observational evidence. The universe might form a simple flat plane extending infinitely, a hypersphere with finite volume but no boundary, analogous to Earth's surface in 2 dimensions, a hyperboloid with negative curvature extending infinitely, or more exotic configurations, like a torus, or even more complex manifolds, with unusual connectivity properties. Observational efforts to determine the universe's topology have focused on searching for patterns in the cosmic microwave background that might indicate light traveling multiple paths around a finite universe, creating a cosmic Hall of Mirrors effect. Current data shows no evidence of such repetition, setting the minimum size of the universe, if finite, at considerably larger than the observable region, at least 120 times the radius of the observable universe, according to the latest analysis. The age of the universe, currently measured at 13.8 billion years, represents another aspect of its totality. This figure refers to the time elapsed since the Big Bang, the initial extremely hot and dense state from which our observable cosmos evolved. However, this measurement applies specifically to our observable region rather than the universe as a whole, which might contain regions of different ages if cosmic inflation operated unevenly across larger scales. The question of what existed before the Big Bang transcends conventional cosmology, as time itself appears to have originated along with space, matter, and energy at this initial moment. Some theoretical frameworks suggest possibilities including quantum fluctuations in a pre-existing state, cyclic models with repeated expansion and contraction, or branching from parent universes through processes analogous to reproduction. These models remain speculative, existing at the boundary between physics and metaphysics, beyond current observational verification. The universe's long-term fate provides another perspective on its overall nature. Current observations indicate accelerating expansion driven by dark energy, a mysterious repulsive force permeating all space. If this acceleration continues indefinitely, as most models predict, the universe will expand forever, with galaxies beyond our local group eventually receding beyond observational reach as space stretches faster than light can travel across it. In this scenario, the universe as a whole continues to exist indefinitely while becoming increasingly diffuse, cold, and eventful, approaching but never quite reaching a state of maximum entropy or heat death. Alternative scenarios, now considered less likely based on observational evidence, include the Big Crunch, where expansion eventually reverses into contraction, ultimately compressing all matter back into a state similar to the Big Bang, potentially initiating a new cycle of expansion. Another possibility, the Big Rip, proposes that accelerating expansion eventually becomes so intense that it tears apart atoms themselves, disintegrating all structure down to the subatomic level. These divergent possibilities highlight our uncertainty about the universe's ultimate nature and evolution, despite considerable observational evidence regarding its current state. The relationship between the observable universe and the universe as a whole creates interesting philosophical tensions regarding knowledge and existence. The observable universe represents the extent of what we can potentially see and measure, while the universe as a whole includes regions forever beyond observational reach. This raises questions about whether unobservable regions should be considered part of scientific cosmology or relegated to metaphysical speculation, despite emerging from the same theoretical frameworks that successfully explain observable phenomena. The concept of a multiverse extends these tensions further, suggesting that our universe might represent just one of countless universes with different physical constants, dimensions, or laws. These other universes would exist beyond not just our observable horizon, but beyond any possible causal connection to our reality, raising profound questions about their ontological status and whether they belong in scientific discourse despite their intrinsic unobservability. String theory, a leading candidate for reconciling quantum mechanics with general relativity, suggests the possible existence of a landscape containing perhaps 10 to the 500th distinct vacuum states, each corresponding to a universe with different fundamental properties. This vast range of possibilities has led some theorists to invoke the anthropic principle, suggesting that we observe a universe with our particular physical constants, because only such universes can support observers. Critics argue that such reasoning threatens to undermine the predictive power of physical theory by replacing specific predictions with probabilistic reasoning across an effectively infinite ensemble of unobservable alternatives. The boundary between science and philosophy becomes particularly permeable when discussing the universe as a whole. Questions about why the universe exists at all, why it has the specific properties we observe rather than others, and whether its existence requires explanation, transcend conventional scientific methodology while emerging naturally from scientific investigation. The universe as a complete entity exists at the intersection of empirical observation, mathematical modeling, philosophical analysis, and even theological consideration, requiring an integrated approach drawing on multiple disciplines and perspectives. Mathematical physicist Roger Penrose has proposed a model called conformal cyclic cosmology, suggesting that our universe represents just one aeon in an infinite sequence, with each aeon's remote future connecting to the next aeon's Big Bang through a conformal transformation that matches the infinitely expanded state of one universe with the infinitely compressed state of the next. This model potentially identifies certain patterns in the cosmic microwave background as remnant signals from a previous cosmic aeon, providing a rare example of a theory predicting potentially observable consequences from beyond our conventional cosmic horizon. Other theoretical approaches suggest that what we perceive as the universe constitutes just one manifestation of a more fundamental quantum reality, potentially including branches representing all possible outcomes of quantum events. According to the many worlds interpretation of quantum mechanics, the universe continually divides into parallel branches for each possible quantum outcome, creating a vast and ever-growing tree of parallel realities. While these branches exist within a larger mathematical structure called Hilbert space, rather than conventional space-time, they represent another conception of the universe's potential totality beyond our observational capabilities. Theoretical physicist Max Tegmark has proposed a mathematical universe hypothesis, suggesting that physical reality itself represents nothing more or less than mathematical structure. According to this perspective, our universe corresponds to just one particular mathematical system among infinitely many possibilities, with other mathematical structures manifesting as different types of universes with properties potentially beyond our ability to conceptualize within our familiar physical framework. This approach reframes questions about the universe's size or shape as questions about the scope and nature of mathematics itself, suggesting that physical reality might be vastly larger and more diverse than conventional cosmology indicates. Information provides another framework for conceptualizing the universe as a whole. Some theoretical approaches, including those related to quantum information theory and holographic principles, suggest that the universe's fundamental nature involves information processing rather than merely matter and energy distribution. The total information content of the observable universe, estimated at approximately 10 to the 120th bits, might represent just a small subset of a much larger informational structure encompassing regions beyond our horizon, or even manifestations beyond our conceptual framework. The holographic principle, emerging from studies of black hole thermodynamics and string theory, suggests that all information contained within a volume of space can be represented on its boundary surface, similar to how a two-dimensional hologram can represent a three-dimensional image. Applied to the universe as a whole, this principle suggests that our three-dimensional reality might represent the projection of processes occurring on a distant two-dimensional surface, fundamentally reframing our understanding of cosmic dimensionality and structure. Consciousness introduces yet another dimension to considerations of the universe as a whole. Some philosophical perspectives, including variants of idealism and panpsychism, suggest that consciousness or experiential properties might constitute fundamental aspects of reality, rather than merely emergent phenomena from physical processes. If such perspectives have merit, the universe's totality would encompass not just physical structure, but experiential dimensions, potentially transcending our current scientific frameworks, adding another layer to considerations of cosmic scale and nature. The question of uniqueness pervades discussions of the universe as a whole. Is our universe unique? the only one that exists or could exist? Or does it represent just one instantiation among countless alternatives, selected through processes beyond our current understanding or existing simultaneously within a larger multiverse structure? This question connects to deeper philosophical issues regarding necessity, contingency, and the ultimate source of physical law, transcending purely empirical investigation while emerging naturally from our efforts to comprehend cosmic totality. The concept of beauty or elegance in physical theory influences how scientists approach models of the universe as a whole. Throughout the history of physics and cosmology, theories demonstrating mathematical elegance, symmetry, simplicity, and explanatory power have generally proven more successful than ad hoc or unnecessarily complicated alternatives. This aesthetic dimension guides theoretical development when direct observational evidence remains unavailable or incomplete, as inevitably occurs when considering regions beyond our cosmic horizon. The relationship between physical law and cosmic structure raises fascinating questions about necessity and contingency. Do the specific physical constants and laws we observe represent the only consistent possibility determined by mathematical necessity? Or do they constitute just one set among countless alternatives, selected through processes beyond our current understanding? This question connects directly to considerations of the universe's uniqueness or multiplicity, with profound implications for how we understand its fundamental nature. The anthropic principle introduces a potential selection effect into discussions of the universe as a whole. This principle notes that we necessarily observe a universe compatible with our existence, regardless of whether such universes constitute the majority or a tiny minority of all possible cosmic configurations. In its weak form, this principle serves primarily as a reminder of observational bias. In stronger forms, it can suggest that our universe's apparent fine-tuning for life requires explanation through either purposeful design or the existence of a vast multiverse containing all possible configurations, with observers inevitably finding themselves in the rare regions suitable for life. The question of whether the universe has a purpose or meaning transcends scientific methodology, while inevitably arising from contemplation of its totality. Science can describe the universe's structure, composition, origin, and evolution with increasing precision, but remains methodologically silent on questions of ultimate purpose or value. These questions belong to philosophy, theology, and human meaning-making more broadly, highlighting the limitations of purely scientific approaches when contemplating the universe as a complete entity with potential dimensions beyond physical description. The totality of the universe raises profound questions about human significance. Our observable universe spans 93 billion light-years, containing approximately 2 trillion galaxies, each with hundreds of billions of stars. Earth represents a minuscule fraction of this vastness, and humanity an even smaller component of Earth's biomass. This perspective might suggest human insignificance within cosmic scales. Alternatively, consciousness and intelligence might represent rare and significant emergent properties within an otherwise largely mindless cosmos, providing a counterbalance to purely size-based assessments of importance. The discovery that dark energy and dark matter constitute approximately 95% of the universe's total energy content highlights how much remains unknown about cosmic totality, despite centuries of astronomical progress. These mysterious components, detected only through their gravitational effects on visible matter and cosmic expansion, remind us that our understanding remains profoundly incomplete. The universe as a whole likely contains aspects, dimensions, or properties currently beyond our detection capabilities or conceptual frameworks, suggesting epistemic humility when contemplating cosmic totality. The accelerating expansion of the universe, driven by dark energy, creates an interesting temporal dimension to considerations of cosmic totality. As expansion accelerates, galaxies beyond our local group will eventually recede beyond our observational horizon, disappearing from view as space stretches faster than light can travel across it. In the far future, observers would inhabit a dramatically different observable universe, containing just a few dozen galaxies, rather than the trillions visible today. This evolution highlights how the observable portion of cosmic totality changes over time, with different epochs offering different windows into the larger whole. As we approach the conclusion of our scale journey, the question, "What is the biggest thing in the universe?" transforms from a straightforward inquiry about spatial extent to a deeper exploration of totality itself. If the universe extends infinitely, as some models suggest, it has no size in conventional terms, being neither big nor small, but simply unlimited. If finite, its total volume would constitute the largest possible spatial entity, though potentially just one component of a larger multiverse structure, transcending simple volumetric measurement. The universe's age, approximately 13.8 billion years since the Big Bang, provides another perspective on its scale. This duration represents an infinitesimal fraction of its potential future timeline, which might extend for trillions of years as stars gradually exhaust their fuel, galaxies disperse, and black holes slowly evaporate through Hawking radiation. The universe we observe today represents just one moment in an ongoing process of evolution, a brief transitional period between its extremely hot, dense beginning and its potentially cold, diffuse future. The question dissolves because the universe is not just big, it may be without limit. As our exploration of cosmic scale reaches its logical conclusion, we confront the possibility that the universe as a whole transcends conventional measurement entirely. If infinite in extent, containing endless galaxies across boundless space, the universe exists beyond the categories of big or small, which require comparison with something else. If part of a larger multiverse structure or mathematical landscape, its significance derives not from spatial extent, but from its place within a more fundamental reality, potentially beyond human comprehension. This dissolving of our initial question represents not failure but transcendence, moving from quantitative measurement to qualitative understanding of the universe's nature. Throughout our journey, from human scale to cosmic totality, we've witnessed how each increase in scale reveals not just larger versions of familiar objects, but qualitatively different types of structure, different organizational principles, different relationships between components. The universe as a whole represents the ultimate expression of this progression, potentially transcending size itself to exist as boundless totality beyond simple dimensional characterization. This perspective invites not frustration but wonder, not disappointment but awe at a cosmos simultaneously comprehensible through scientific investigation, yet ultimately transcending complete human understanding. The universe reveals itself to us through light crossing billions of light years, through subtle patterns in ancient radiation, through the dance of galaxies tracing gravitational fields across cosmic distances. Yet it maintains mysteries beyond our observational horizons, potentially containing dimensions, structures, and properties forever beyond direct detection, yet hinted at through theoretical implications and mathematical consistency. As we approach the conclusion of our cosmic journey, this tension between the known and unknown, the observable and the merely inferable, the comprehensible and the transcendent, defines our relationship with the universe as a whole. We have mapped its observable extent with remarkable precision, identified its major components, traced its evolution from quantum fluctuations to the complex cosmic web. Yet we recognize these achievements as partial glimpses of a potentially boundless reality, extending far beyond our observational capabilities and perhaps beyond our conceptual frameworks. The question dissolves, not into meaninglessness, but into a deeper appreciation of cosmic reality. The universe is not merely big, it may be without limit, not just in spatial extent, but in the depth and richness of its structure across multiple dimensions of existence. In seeking the biggest thing, we discover not a definitive answer, but an invitation to ongoing exploration, an endless frontier of discovery extending across billions of light years and billions of years, challenging humanity to continuously expand its understanding of the greatest structure of all, the totality we call the universe. In seeking the biggest thing, we often find the smallest part of ourselves. As our journey through cosmic scales approaches its conclusion, we turn our attention from the external universe to the internal landscape of human consciousness. Why does cosmic scale captivate us so profoundly? What explains our persistent fascination with the vastness of space, with objects and structures whose dimensions exceed our direct experience by orders of magnitude? This attraction to the immense, evident throughout human history from ancient myths to modern astronomy, reveals something fundamental about human cognition, imagination, and our place within the cosmic context. Our fascination with size begins in childhood, when the world appears enormous and we ourselves small within it. Children naturally compare sizes, marveling at tall buildings, large animals, or vast natural formations. This early calibration of scale helps develop spatial reasoning and situational awareness necessary for navigating the physical environment. The comparison continues into adulthood, now extended beyond the immediate environment to encompass mountains, oceans, planets, and beyond, reflecting our innate tendency to organize experience through relative measurement. The psychological impact of encountering truly vast scales produces a distinct emotional response, sometimes called the overview effect, when experienced by astronauts viewing Earth from space, or the sublime in philosophical aesthetics. This response combines awe, wonder, slight fear, and a sense of one's own smallness within a larger context. Unlike simple fear, which prompts withdrawal, or simple pleasure, which encourages approach, this complex emotion encourages both continued engagement and humility, a recognition of significance beyond the self that nevertheless invites rather than repels further exploration. This emotional response serves important psychological functions. By temporarily diminishing the perceived importance of personal concerns against the backdrop of cosmic scales, contemplation of vastness can provide perspective during difficult circumstances. Problems that seem overwhelming when viewed through the lens of immediate experience often appear more manageable when considered against astronomical backdrops. The popular saying, "Don't sweat the small stuff," gains particular resonance when small stuff includes not just minor annoyances, but potentially the entirety of human existence viewed against the cosmic scale. Evolutionary psychology suggests potential adaptive value in our fascination with scale. Early humans who maintained awareness of their environment at multiple scales, from immediate surroundings to broader geographical contexts, likely navigated their world more successfully than those with narrower perceptual focus. The ability to shift between scales, to simultaneously hold awareness of immediate dangers and larger patterns, conferred survival advantages in environments with threats and opportunities operating at different distances and timescales. Our fascination with cosmic scales might represent the extreme extension of this adaptive capacity, now applied to contexts far beyond those in which it evolved. Cultural dimensions further shape our engagement with cosmic scale. Different civilizations throughout history have constructed distinct frameworks for understanding human placement within larger contexts, from ancient cosmologies depicting Earth as central to hierarchical arrangements of celestial spheres, to modern scientific models revealing Earth as one planet among billions, within one galaxy among trillions. These frameworks, whether scientifically accurate or not by current standards, satisfy a persistent human need to situate ourselves within comprehensible structures extending beyond immediate experience. The historical progression of these frameworks reveals a pattern of continuous expansion, with each civilization's conception of cosmic scale typically exceeding its predecessors. Ancient Mesopotamian cosmologies depicted Earth floating in a cosmic ocean, surrounded by celestial bodies. Greek astronomers calculated the Earth's circumference and estimated, albeit incorrectly, the distances to the Sun and stars. Medieval European models placed Earth at the center of nested celestial spheres extending outward to the fixed stars. Each framework represented the universe as larger than previously conceived, yet still comprehensible within human terms. The scientific revolution, beginning in the 16th century, accelerated this expansion dramatically. Copernicus relocated Earth from the cosmic center to one planet among several orbiting the Sun. Galileo's telescope revealed Jupiter's moons and countless previously invisible stars. Later observations established the Sun as one star among many within the Milky Way, and eventually the Milky Way as one galaxy among billions in an expanding universe. Each discovery pushed cosmic scale further beyond intuitive comprehension, while simultaneously bringing these scales within theoretical understanding through mathematics, physics, and astronomy. This tension between intellectual comprehension and intuitive grasp defines our modern relationship with cosmic scale. We can state that light travels approximately 300,000 kilometers per second and that the observable universe spans 93 billion light-years, but we cannot intuitively comprehend such speeds or distances. They exist for us as mathematical abstractions, conceptually accessible but experientially transcendent, understood but not truly felt, except through metaphor, visualization, and imaginative extension of familiar experiences. The media through which we encounter cosmic scale shapes our emotional and intellectual response. Early astronomers observed celestial bodies directly through naked eye observation, limiting the range of accessible scales, but providing immediate sensory connection. Telescopes extended observational range while introducing technological mediation between observer and observed. Modern astronomy relies on instruments detecting radiation across the electromagnetic spectrum, including wavelengths invisible to human eyes, further abstracting observation from direct sensory experience. Visual representations play crucial roles in translating these abstract measurements into comprehensible forms. Scale models, diagrams, animations, and comparisons to familiar objects help bridge the gap between mathematical understanding and intuitive grasp. When we represent the sun as a basketball and Earth as a peppercorn, or when we visualize the solar system through a scale model stretching across a city, we translate abstract dimensions into spatial relationships accessible to direct experience. These translations never capture cosmic reality fully, but provide essential cognitive scaffolding for approaching scales beyond direct perception. Professional astronomers develop specialized cognitive frameworks for navigating cosmic scales. They think comfortably in light years, parsecs, and megaparsecs, shifting between scales as naturally as others might shift between meters and kilometers. This facility comes through prolonged engagement with astronomical data, mathematics, and visualization techniques, demonstrating how human cognition can adapt to work effectively with scales far beyond those encountered in everyday experience. Yet even the most experienced astronomer remains limited by evolved cognitive architecture, requiring conceptual tools to bridge the gap between calculation and comprehension. The contemporary proliferation of cosmic imagery through digital media has democratized access to visualizations of astronomical scale. High-resolution photographs from space telescopes, computer-generated fly-throughs of the cosmic web, and interactive digital models allow non-specialists to explore cosmic structures visually, if not physically. These visualizations, while inevitably simplified and often artistically enhanced, provide experiential engagement with scales otherwise accessible only through abstract mathematics, extending humanity's perceptual range far beyond biological limitations. This extended perception operates across time as well as space. Human perceptual systems evolved to handle timescales relevant to immediate survival, from fractions of seconds needed to dodge threats to the several decades of a human lifespan. Astronomical processes unfold over timescales ranging from milliseconds, pulsar rotations, to billions of years, galaxy evolution, requiring conceptual translation, similar to that used for spatial scales. When we compress cosmic evolution into brief animations or extend our perspective through mathematical projection, we transcend our temporal as well as spatial limitations. The vastness of cosmic scale inevitably raises questions about human significance. Does our minuscule size relative to the universe indicate our cosmic insignificance? Or does consciousness and intelligence represent something rare and precious within an otherwise largely mindless cosmos? Different philosophical, religious, and scientific traditions offer divergent answers to these questions, reflecting how cosmic scale intersects with our search for meaning and purpose within the universe we inhabit. Many religious traditions have addressed this tension by positioning humans as spiritually central despite physical marginality, created in divine image or possessing souls, connecting us to transcendent reality beyond physical limitation. Scientific perspectives sometimes emphasize the remarkable improbability of intelligent life emerging through evolutionary processes, suggesting that consciousness might represent something genuinely rare and significant, despite occupying infinitesimal cosmic volume. Others argue that intelligence likely exists abundantly throughout the universe, given the vast number of potentially habitable planets, further contextualizing human existence within larger patterns. The cognitive dissonance created by recognizing both our physical insignificance and our capacity to comprehend cosmic scales creates fertile ground for philosophical contemplation. We occupy an interesting middle position in the scale hierarchy, capable of studying both quantum particles and galactic superclusters, positioned neither at the smallest nor largest extremes, but in a region of scale, allowing perspective in both directions. This position might represent mere coincidence, or might reflect something meaningful about conscious intelligence's natural scale of emergence and operation. Our fascination with cosmic scale deeply shapes cultural production across numerous domains. Literature abounds with works exploring human positioning within vast cosmic contexts, from ancient epic poems describing celestial journeys to modern science fiction imagining interstellar civilizations. Visual arts depict cosmic vastness through various techniques, from symbolic representation in ancient artifacts to photorealistic digital renderings based on astronomical data. Music attempts to capture cosmic scales through compositions, evoking celestial movement and harmony, sometimes directly incorporating astronomical data through techniques like sonification. These cultural expressions serve multiple functions simultaneously. They translate abstract astronomical knowledge into forms accessible through emotional and aesthetic experience. They explore philosophical implications of human existence within cosmic immensity. They inspire wonder, awe, and curiosity, motivating further scientific exploration. And they provide shared reference points for collective contemplation of questions transcending individual experience, creating community around common wonder, despite potentially divergent interpretations. The practical utility of engaging with cosmic scale extends beyond aesthetic appreciation or philosophical contemplation. Developing comfort with different orders of magnitude strengthens quantitative reasoning applicable across many domains. The perspective gained through astronomical awareness may contribute to environmental consciousness by contextualizing Earth as a rare habitat within an otherwise largely inhospitable cosmos. And the intellectual humility fostered through contemplating scales beyond intuitive grasp may generalize to other areas requiring recognition of cognitive limitations when approaching complex problems. Digital technologies increasingly enable not just passive viewing but active exploration of cosmic scales. Interactive applications allow users to zoom seamlessly from human scale to galaxies or subatomic particles, manipulating time and perspective to explore relationships between objects of radically different dimensions. Virtual reality technologies promise even more immersive experiences, potentially allowing users to experience cosmic scales through simulated spatial navigation, rather than merely conceptual understanding. Though complete experiential translation remains fundamentally limited by our evolved perceptual systems, scientific institutions recognize the public's fascination with cosmic scale and increasingly incorporate scale-focused elements in educational programming. Planetariums project cosmic vastness onto domed ceilings, creating immersive experiences that simulate space travel across astronomical distances. Museums construct scale models, allowing visitors to walk through miniaturized solar systems or greatly enlarged atomic structures. These educational approaches leverage innate fascination with scale to build scientific literacy and engagement, translating abstract measurements into memorable spatial experiences. The future of humanity's engagement with cosmic scale may extend beyond conceptual understanding or simulated experience toward direct exploration. Current space programs represent initial ventures beyond Earth, still limited to our immediate planetary neighborhood. Future technologies might enable exploration across greater distances, potentially including interstellar travel over generational timescales. Such exploration would progressively incorporate larger cosmic scales into direct human experience, though the vastness of intergalactic space would likely remain beyond practical, physical navigation, regardless of technological advancement. More immediately, ongoing astronomical research continues expanding our understanding of cosmic scale through projects like the James Webb Space Telescope, large-scale galaxy surveys, and gravitational wave observatories. These investigations reveal ever more detail about the universe's structure across multiple scales, from exoplanetary systems to the cosmic web. Each discovery further refines our understanding of cosmic scale, while simultaneously revealing new questions and mysteries, ensuring continued engagement across scientific and popular domains. In seeking the biggest thing, we often find the smallest part of ourselves. This paradoxical relationship between cosmic vastness and human consciousness reveals something profound about our nature as meaning-seeking beings. We are physically minuscule yet cognitively vast, occupying infinitesimal cosmic volume, while containing mental models of the entire observable universe. This tension between physical limitation and conceptual reach defines the human condition perhaps more fundamentally than any other single characteristic. Our fascination with cosmic scale ultimately reflects our uniquely human capacity to transcend immediate experience through imagination, abstraction, and symbolic thought. We remain physically bound to human scale, experiencing reality through senses evolved for terrestrial navigation and social interaction. Yet mentally we travel across billions of light years, conceptualize structures larger than galaxies, and contemplate time frames exceeding billions of years. This cognitive flexibility, this capacity to shift perspective from immediate surroundings to cosmic totality, represents one of humanity's most remarkable and distinctive capabilities. This capability carries both opportunity and responsibility. Understanding cosmic scale positions us to appreciate Earth's rarity as a life-supporting environment within the vastness of space, potentially motivating more sustainable relationship with our planetary home. Recognizing our physical insignificance within the cosmic context may foster humility, tempering tendencies towards self-importance that sometimes drives destructive behavior. Yet simultaneously acknowledging the significance of consciousness as a rare capacity for self-reflection within an otherwise largely mindless cosmos may inspire appropriate appreciation for human potential and responsibility for its wise application. As our journey through cosmic scales concludes, we recognize that the answer to our initial question, "What is the biggest thing in the universe?" reveals as much about the questioner as about the cosmos itself. Our capacity to ask such questions, to systematically investigate reality across scales from quantum particles to superclusters, and to find wonder and meaning in the answers we discover, may represent something truly significant within the universe, regardless of our physical size. In seeking the biggest thing, we discover our uniquely human capacity to transcend scale itself through consciousness, imagination, and the quest for understanding. The biggest thing in the universe is not just a number. It is the feeling we get when we try to imagine it. A quiet awe, a limitless wonder. Sleep now, under a sky that stretches beyond all knowing. As our journey through cosmic scales comes to its conclusion, we return to our original question: what is the biggest thing in the universe? Throughout our exploration, we have traveled across orders of magnitude almost beyond comprehension, from human scale to planets, stars, galaxies, superclusters, and the vast cosmic web stretching across billions of light years. We have contemplated structures so enormous that light itself, traveling at 300,000 kilometers per second, requires billions of years to cross them. We have considered the observable universe as a whole, spanning 93 billion light-years in diameter and containing trillions of galaxies. And we have ventured into theoretical terrain beyond our observational horizon, contemplating the possibility of infinite space, multiple universes, and realities transcending our familiar dimensions. This journey has revealed not a single definitive answer, but a progression of ever larger structures, each operating according to different organizing principles, each challenging our comprehension in unique ways. What appeared enormous at one scale became minuscule at the next, with each transition revealing new patterns, new relationships, new wonders. Earth, immense compared to human scale, becomes a tiny mote compared to the sun. The sun, a cosmic furnace converting millions of tons of matter to energy each second, represents just one ordinary star among hundreds of billions in the Milky Way. Our galaxy, spanning 100,000 light-years, appears as a mere point of light within the vast cosmic web stretching across billions of light-years. And even the most enormous structures we have identified might represent infinitesimal portions of a boundless cosmos, extending far beyond our observable horizon. Perhaps the most profound insight emerging from our scale journey involves not the specific dimensions of cosmic structures, but the remarkable fact that we can comprehend them at all. Human beings, confined to bodies measuring less than 2 meters tall and brains weighing approximately 1.5 kilograms, can nevertheless contemplate realities spanning billions of light years and processes unfolding over billions of years. Through mathematics, observation, theory, and imagination, we transcend our physical limitations to develop mental models of cosmic scales, far beyond direct experience, revealing something extraordinary about consciousness itself. This capacity for transcendence through understanding represents one of humanity's most distinctive and remarkable characteristics. We exist physically at tiny scale, yet cognitively encompass the observable universe. We live for mere decades, yet comprehend cosmic evolution spanning billions of years. We perceive directly only visible light, yet develop instruments and mathematics revealing radiation across the electromagnetic spectrum and beyond, including gravitational waves rippling through space-time itself. These achievements testify to something significant about human consciousness, regardless of our physical insignificance within cosmic immensity. The quest to identify the biggest thing ultimately leads not to a simple measurement, but to deeper questions about reality itself. Is the universe finite or infinite? Does it have a boundary or edge? Does it represent the totality of existence, or just one component of a larger multiverse? These questions transcend purely empirical investigation, existing at the intersection of astronomy, physics, mathematics, and philosophy. They remind us that scale itself represents a human construct, a framework we impose upon reality to make sense of it, rather than an intrinsic feature of the cosmos independent of our observation and comprehension. This realization invites a certain epistemic humility regarding our cosmic understanding. The universe exists independently of our ability to observe or comprehend it, potentially containing dimensions, structures, and phenomena forever beyond our epistemic reach. Our best theories and observations might reveal just a tiny fraction of a vastly larger and more complex reality. The observable universe itself represents not the totality of what exists, but merely what light has had sufficient time to reach us since the Big Bang, limited by the finite speed of light and the finite age of the universe. Yet rather than discouraging further exploration, this humility inspires continued investigation, recognizing each discovery as one more piece in an endless cosmic puzzle. Throughout human history, our understanding of cosmic scale has continuously expanded, from Earth-centered models encompassing just the visible planets to modern cosmology spanning billions of light years. Each expansion revealed previously unimagined structures while demonstrating the limitations of earlier perspectives. Our current boundary at the observable horizon likely represents just one stage in an ongoing expansion of understanding, with future theoretical and observational developments revealing new dimensions of cosmic structure beyond current conceptualization. The emotional impact of contemplating cosmic scale provides another important dimension of our journey. The combination of awe, wonder, slight fear, and recognition of our own smallness within vast contexts creates a distinctive experience, sometimes called the sublime in philosophical aesthetics. Unlike simple fear, which prompts withdrawal, or simple pleasure, which encourages approach, this complex emotion encourages both continued engagement and humility, a recognition of significance beyond the self that nevertheless invites, rather than repels, further exploration. This emotional response serves important psychological functions beyond mere aesthetic appreciation. By temporarily diminishing the perceived importance of personal concerns against the backdrop of cosmic scales, contemplation of vastness can provide perspective during difficult circumstances. Problems that seem overwhelming when viewed through the lens of immediate experience often appear more manageable when considered against astronomical backdrops spanning billions of light years and billions of years. Without diminishing genuine human suffering, cosmic perspective can sometimes help distinguish between truly significant concerns and those magnified by limited temporal or spatial focus. Perhaps most profoundly, our journey through cosmic scales reveals something essential about the human condition itself. Simultaneously, physically minuscule, yet cognitively vast, occupying infinitesimal cosmic volume while containing mental models of the entire observable universe. This tension between physical limitation and conceptual reach defines the human experience perhaps more fundamentally than any other single characteristic, positioning us within reality as beings capable of transcending immediate circumstances through understanding, imagination, and wonder. As you drift towards sleep listening to these words, imagine yourself suspended between scales, simultaneously a collection of atoms, a biological organism, a conscious individual, a member of human society, an inhabitant of Earth, a mote within the solar system, a spark within the galaxy, a momentary configuration of matter and energy within a universe spanning billions of light years. Each perspective reveals different truths, different patterns, different significance. None alone captures the full reality of existence. Yet together, they create a multi-dimensional understanding richer than any single-scale perspective could provide. Allow your consciousness to float freely between these scales, recognizing both your physical tininess within cosmic immensity and your cognitive vastness, capable of comprehending scales far beyond direct experience. Feel the strange liberation that comes from recognizing your simultaneous significance and insignificance, the paradoxical freedom emerging from accurate self-placement within the cosmic context. This balanced perspective, neither exaggerating human importance nor dismissing the genuine significance of consciousness within an otherwise largely mindless cosmos, provides solid foundation for navigating existence with appropriate humility and wonder. As your breathing slows and your thoughts drift toward dreams, remember that the stars above you now have shone for billions of years before your birth and will continue shining for billions after your passing. The atoms comprising your body formed in stellar furnaces long vanished, the calcium in your bones and iron in your blood, forged through nuclear fusion within stars that exploded billions of years ago, scattering these elements across space to eventually incorporate into planets, oceans, forests, and finally into conscious beings capable of contemplating their stellar origin. You exist as a momentary arrangement of matter with roots extending across cosmic time and space, simultaneously ephemeral and eternal. The quest for the biggest thing reveals finally not a specific measurement but an orientation toward reality, an appreciation for scale itself as a dimension of understanding. The cosmos exists not as a collection of discrete objects arranged by size, but as an interconnected whole that we perceive differently at different scales of observation. What appears as chaos at one scale reveals remarkable order at another. What seems empty at human perspective teems with activity when viewed at appropriate scale, whether vastly larger or incredibly smaller. The universe reveals its nature not through any single perspective, but through the integration of multiple viewpoints across the full spectrum of possible scales. The biggest thing in the universe is not just a number, it is the feeling we get when we try to imagine it, a quiet awe, a limitless wonder. Sleep now, under a sky that stretches beyond all knowing.